Good morning, everyone. Um, Welcome to the Alberta Health Services AI COP. Look forward to hearing this presentation. Today we've got Michael Lanham. Mike's been in IT, entrepreneur, innovator for 20 years here now. He lives in Calgary. He's done software applications, including games and graphic, web, desktop, engineering, artificial intelligence, GIS, machine learning. At the turn of the millennium, Mike began working with neural networks and evolutionary logarithms in game development. He was later introduced to Unity and has been an avid developer, consultant, manager, and author of multiple games, graphic projects, and books. I had a link on there to some of your books, Mike. Mike's written augmented reality game development, game audio development with Unity, and Learn ARCore. Fundamentals of Google ARCore, and has a ton of experience, and I really look forward to hearing your presentation. Thanks so much, Mike, for offering to do this presentation. I know that takes quite a bit of your time, and we really do appreciate it. So without further ado, I'll pass the screen off to you, Mike. There we go, and welcome.
Okay, thank you very much, Jesse. So I'm just going to be presenting my desktop. It's been a while since I've used links, so just bear with me, guys. Okay. Okay, so yeah, I think it's one of your employees that was going to my meetups that had suggested this to you, Jesse. And typically, I ran a Calgary deep learning meetup. We'd meet every month, get together and do these types of sessions where we'd learn and teach each other deep learning. For the most part, it was just me teaching everybody what I've learned about deep learning over the years and other aspects of data science and stuff like that. So over the course of that and through writing my books and stuff like that, so I've also written 3 books on reinforcement learning. And that transition to reinforcement learning was because I had some interest in deep learning, but also because I had a fair bit of exposure to game programming in the 90s. I was actually a game programmer in the 90s before I entered oil and gas as essentially just a graphics programmer. So most of my time in oil and gas has been spent doing graphics programming projects, sort of engineering pieces, and a lot of that has been working with academics. So again, a lot of my experience has been through data science, and through those things of data science, handling large amounts of data, handling them efficiently and making sense of data is also another reasons why I've come to develop for my skills in deep learning. So this course is really just a quick overview of what deep learning is. I take a more pragmatic approach, and if you guys have any questions or anything, go ahead. Okay, if I hear anybody cut from mute, I'll just assume maybe somebody has a question or something. But if you have a question, just stop me during the presentation is fine. So as just like I said, this course has been derived from a number of presentations I've done. Go ahead if anybody wanted to ask a question. No? Okay. So this course is derived from a number of presentations I've done over the past couple of years on deep learning. A lot of it's hinged from just my pragmatic approach to teaching this stuff. I tried to teach it the way I first learned it, using code and models and stuff like that, but that wasn't very effective. So what I'm going to do here is just go into an example called the Big GAN, using a Big GAN example. So here I'm just going to go into I just have to turn the, there we go. So what I'm going to do is I'm just going into Google Colab. So what if I can just make sure everybody can log into Google Colab on their other screen. So what I'm showing you now is basically how I go to Google Colab. I just type in Google Colab in Google, go to the first link, and you'll be able to open up Google Colab. And in my example here, I'm using the wrong user, so I'm just going to switch to my normal user. And in here, I just have a whole bunch of notebooks that I can save in my Google Drive. And what I'm just going to do is going to go to one example I've run previously and done. This is from the TensorFlow authors. What I'm going to do is I'm just going to say runtime, run all. And this is just a Jupyter notebook, essentially, but it's on Google Collaboratory. Google Colab is a nice platform to train and work with these examples. We'll run through a couple code examples. My intention right now is not to show you the code here, but just to show you the output and examples. So we'll kind of walk through some of the code pieces here a little bit. It is in Python, so it's not too onerous, I guess, if most people are in IT. But really what I want to show is the output of this example. And what it's doing right now is it's just running its model, and it's just generating an output through a GAN, a generative adversarial network. And this GAN was trained on a data class called ImageNet. ImageNet consists of about 2 million images and 1,000 classes. So what we're going to be working through is how to explore and understand how these GANs work at a fundamental level. So essentially right down to how the perceptron functions and how the GAN sort of encodes this stuff and decodes it. So what we're looking at here is an example of the GAN generated some output. Keep in mind, this is not real, but it certainly looks like ice cream, right? The model that's generating this output was trained to be about 300 megabytes, but it doesn't use a database. It's not pulling images from a database. It is just essentially just randomly generating those pictures based on what it's learned. Now I can show you some other examples, and we'll go through and sort of get some understanding of how this works. But for instance, if I go ahead, if somebody has a question.
Hey, Mike, could you help those that aren't familiar with some of the terminology GAN, and then secondly, Jupyter notebooks, and just describe them?
Yeah, so GAN is, we'll cover a lot more of a GAN. It's literally what we're leading up to is this demonstration and how this works. So I was just showing this as a sort of a basic, that's our end goal. So a GAN, or generative adversarial network, is just a form of training deep learning that we'll uncover here as we go. And then, what was your other question? Oh, Jupyter Notebooks. And Jupyter Notebooks is essentially just a nice, helpful platform for running Python in code cells or text cells. So a lot of people use Jupyter Notebooks as a way of documenting their research or their way of doing data science. They're very popular in data science as a way of sort of documenting the things you've done and setting up stuff. The excellent thing about Colab is it has a whole bunch of dependencies already installed for you, the TensorFlow, a whole bunch of other Python dependencies, which is a big issue if you decide to do any of this on your desktop, for instance. So installing a whole bunch of this stuff, all these imports we're doing here, those are all things you'd have to make sure to install that are all coming with Colab, that are all coming with this notebook. Okay, so let me just jump back to the presentation. And so this is going to be our end goal, guys. So just keep that in mind. This is our end goal. This is what we want to get to. Okay, so let me just jump back to the presentation. For some reason, my presentation stopped. So we're just starting with the history of deep learning. And I usually go through the history of deep learning just to sort of emphasize that this technology has been around for a really long time, but it was frowned on by general science just because it sort of, it sort of takes inspiration from the brain and in the way our brain functions in a connected manner. Really, that's it. But I think it's that stigmatism that it's sort of trying to replicate the brain that has been in science for so long that it was sort of frowned on. And there's some other reasons. So one of those other big reasons was in 1969, I think it was, Marvin Minsky published a paper on the XOR problem. Essentially, he used a perceptron to try and solve the XOR problem. and I think most of us are in IT, so we realize what that problem is, and essentially stated that the perceptron could only do just that, could only solve the XOR problem. So from about 1969 till Dr. Hinton came along in the 80s, 86, when he showed that you could multi-layer these perceptrons together and this thing called back propagation would work, is what sort of shot off. So that whole period from 67 to 86 was what we call the first deep learning winter. And that was a whole period where nobody sort of touched deep learning. There was a whole, nobody even looked at this technology. Not that we had the computational power to do what we're doing now with it. And that's some of the things that people are asking, why is this all taking off so much? It's kind of like the perfect storm. We have the computational pieces and all this other pieces have just been brewing for so long. So, and then here, so essentially with the tech, you know, we get into this concept of the 40s, the electronic brain. The perceptron was introduced by Frank Rosenblatt. So if we go back here, there's old
Hey, Michael,
Frank
would it be possible to click on display settings and then switch? Right now we're seeing the
Oh,
presentation view, not the full presentation.
Oh, okay. Sorry, guys.
No problem. Thank you.
Yeah. No, thanks for telling me. Okay. So now, can you see that? Sorry. Do I have to retalk this?
Yeah, perfect.
Okay, good. Yeah, so what I'm showing here is the timeline of the history and events. I guess maybe you didn't see that very well last time, so I'll just hold this up again. Let me just mouse over some of those pieces I was talking about. So here's the XOR problem. Here's Minsky here. I typically red X his diagram because he's been sort of dragged into the Epstein thing, so if nobody's heard about that. So there's actually medals of his picture on it floating around, which I'm sure people aren't too enthused about anymore. But that's just an anecdote. So yeah, so this technology has been around since the 50s, 60s, all the way up to here. We could have been making use of it for some time since then, but we just haven't because of, just, you know, various stigmatisms and other things like that around deep learning. A big one being the XOR problem, which Minsky sort of published his paper about, which caused that first dark age of the AI winter until Hinton came along. And then from there, we got some more traction until about the mid-90s, and then we sort of count that as another winter as well. So that's this period here from 1995 to, some people say about 2006. I say it's closer to about 2008, but again, and then we get this explosion of growth here, right? All the way from 2010 all the way up, all sorts of explosive growth. And a lot of people, you know, believe that we might experience another AI winter. I don't think so. And the big reason for that is because the deep learning now is sort of computationally entrenched into what we do. And what I mean by that is when I was building applications, one of the things I started to look at was actually doing just typical calculations the same way we might do with deep learning and using GPUs and stuff like that, because I could do them almost 1,000 times faster. So even just computationally, these methods are so powerful that I can see them being used in tons of engineering applications and other things, not even using deep learning, for instance. Okay? And it really speaks to a larger AI convergence itself. It's all these things sort of coming together, the data science, the technology itself. You know, gaming has a big part to play in this as well. The GPUs and being able to process large and tons of amounts of data that we're doing now with deep learning. And it's just scaling well. We've recently come across some other ways of CPUing deep learning methods. There's recently this paper out with a method called slide. It uses hash tables. Because as we'll see, deep learning is really just a search problem. And I'll get to that here as we get into the perceptron and look at that stuff. Okay? So here again is a deep learning timeline, some of the bigger things that have occurred through that time. The big one here is back propagation. Okay, Hinton, who's considered the godfather of deep learning, has been instrumental in doing a lot of this stuff, especially through the 90s and the second AI winter. He's continued on as a big proponent of that. Rich Sutton as well. He's had a huge hand in a lot of this with his student David Silver at the U of A. So if we're not all aware that U of A is actually considered #2 in the world as far as reinforcement learning is concerned, just because of Dr. Rich Sutton up there and his most famous student, David Silver. Okay. So compared to other ML AI, deep learning is really taking off because it can crunch massive amounts of data better. And I've sort of alluded to this a couple times already. The GPUs that we can throw at these things, we can, get huge increases in performance over other classical models, but deep learning isn't without its own problems. Deep learning is still very much hinged to the backpropagation algorithm we used, which is dependent on calculus. And I'll talk to that a little bit as we go through. Okay, so really, why deep learning? And again, it's really about performance and other learning algorithms. It really is surpassing those other algorithms. So, if it came right down to a side-by-side comparison between data science, and we think back to the late 90s, deep learning was still struggling because computationally it was very much, handicapped in a way. Now those handicaps are all gone. It's sort of just taking off full force. And here's some other things, just some other graphs showing performance improvements and what we're seeing in GPU cards, etc. And this is just even going through the roof even more, as well as improving accuracy. For a certain class of models, this is the ImageNet classification. So this is the ImageNet classification exercise, which was an exercise in 2012 that they built AlexNet. AlexNet was built by a team led by Hinton. Sorry, I don't know the actual author's name, but that was the use of convolutional neural networks, which we'll get to, which was the other sort of big improvement that sort of blew up deep learning. It was that ImageNet classification and then a drastic improvement in accuracy and being able to detect images, which really blew up deep learning as well. Okay. And then as far as deep learning frameworks, and we'll get into this a little bit more, TensorFlow, Keras, PyTorch is becoming a very quick behind this, and some other deep learning frameworks. Okay. I'm going to skip this slide.
This call may be recorded for quality assurance, accuracy, and training purposes. To activate a VPN token,
are we recording this?
If you are an auto plan broker,
I don't know who's on there, but if you can mute, please, that'd be great. Thank you.
Okay, so I have a quiz that if we want to stop for a quick 2-minute break and then I can jump on to the next section. Jesse, is that
Absolutely
fine? Or?
Yeah, of course, yeah.
So there's the URL there, or I guess I can copy it and put it in the chat window as well. Here, I just have to escape. So the reason I started giving these quizzes, and this quiz, you don't, there is a spot to put your name and stuff like that, etc., but don't feel that you have to. It's just there for if you want to put the quiz in or something, or if you want to print out the certificate after. Where's the chat?
It should be under Microsoft link, and then you have to quick chat it. There we go. Great.
I'm still sharing my screen, right?
Mm-hmm. Yes, you are. Yeah.
Yeah, okay. So I'll just give one more minute and then we'll just quickly go over. I think it's only just the first test is 5 questions. And I may or may not have hit all the high points anyways. So these will just be a reinforcement of what I meant to discuss.
Well, Michael, I didn't do so well.
Okay. Okay. Well, that might have been the teacher rushing through the content. So let's see. So who first invented the perceptron model in 1958? Well, that was Frank Rosenblatt. Okay. Who is often blamed for creating the first deep learning AI winter? Well, that's Marvin Minsky. So we usually pin that on. Who is considered the godfather of deep learning? That is Geoffrey Hinton. And what catalysts have helped develop and promote deep learning? And essentially, all of those are all the catalysts that have sort of helped. And during what time period is acknowledged as the second AI winter? And we usually take that to be the 1995 to 2008 is somewhere closer to that. The other times just don't line up very well. And so this one here, which is the following is not a deep learning framework. We didn't really cover that. Coffee is that one. There is a deep learning framework called CAFE. So that was a sort of a trick question. And about what time date was TensorFlow first released? Again, that was another, nothing we really covered, less detailed. I believe the answer is 2015. So I should give you the right answer for that, shouldn't I? Okay. Let's get back into the presentation here. Okay, so now we're going to go into what I typically do is the hands-on part of the exercise, but we're not in a big classroom, so we can't do that. So I hopefully have a few tools that can hopefully help with this, but we're going to get into the perceptron now and how actually the sort of the engine of the whole deep learning model works. Like I said, the perceptron is really based on the biological neuron from a connection of, or the way it sort of connects itself, I guess, is the inspiration. Now, realistically, our brains think and learn and stuff like that vastly differently. A lot of people, I guess it's sort of suggested now that we actually learn more as we sleep than actually doing something. So there's a lot of sort of theories and playing with this stuff. And we are getting back to very much going back to the neuron itself to try and figure out these problems and understand it even further. So it's interesting. But what we have here, so that's that first perceptron model. This is a derivation from Minsky, which he sort of refined this a little bit, and he added these sort of 3 inputs, 3 weights, and an output as y. And then from here, we have the what we sort of classically refer to as our perceptron model now. So we have this sort of constant value at the top, which we refer to as the bias, and then each of our inputs come through here. So in our problem, if it's an image, we would shoot all the pixels from an image into one perceptron. So each perceptron would get all the pixels of an image. And I'll go over this again. And then with that, there's all these weights as well. These weights are multiplied by the input value, and then all of this is summed up. And I'll go through this again, and then this is run through an activation function or not. And again, we'll go through this, okay? So this is sort of the concept of how it works. The values are fed in, and then we can do these sort of classification or regression exercises, right? Or classification is another just form of logistic regression. Okay, and this is sort of it visualized. Okay, you can see the weights are coming in and getting multiplied, summed up, and then in getting output. Okay, we'll do something similar as well. Okay, so this is going to be our simple model of a perceptron. We're going to use this in an exercise or game that I typically use. Okay. So we're gonna simulate inputs and how we need to learn the weights to develop this model that'll learn our problems. So the problem we're going to face here, so when we have an input come in, say the input is a 1, it comes in, we multiply that 1 times the half, that means it's a half, and then this is multiplied 1 times 1 equals 1, right? So then we have 1 times 1 equals 1, and x1 times w1 equals 0.5. Our total sum at this point is 1.5, and if we have an activation function, we'll activate, but in this case, we don't have an activation function, so that 1.5 just flows right out. That's essentially how the basic perceptron model works. Is there any sort of questions? We'll look at that a little closer here shortly. No? Okay. In typical image problems, this is an example of the IMNIS set. We'll look at this problem here shortly from a Python programming perspective. This is an image that we've sort of taken apart, and you can see each of the pixel values of the image are shown there. Now we can see the middle values, we're using 0 to 255 to represent the grayscale values of the pixels here, and they all represent the values here. These all get fed into, there's 784 total pixels, all these pixels would get fed into a neural network. Each of these nodes here would represent a perceptron, okay? Notice that each pixel value goes to each perceptron, okay? And then this would flow through the rest of the network. We'll get to how this flows through the rest of the network here shortly. But just to understand that our whole image here is just sort of flattened out and pushed into our deep learning network. So we're going to simplify this problem greatly, and we're going to use 3 images. We have these 3 images, one that is completely filled, and we want to classify it as filled. We have a mixed one that we want to classify as mixed with a value of 0.5, and we have an empty one that we want to classify as 0. Okay, that's our problem. So in our model, we're going to feed in each of these 3 images separately into our model, and then we're going to find the weights that give us these values. Okay. So when we pass in image 1, we're going to pass a 1 to x1 and a pass a 1 to x2. Remember, we'll still modify the bias, so we'll have 3 weights we have to find to give us a value of 1. Okay? The same goes for the mixed image. But remember, these 3 weights have to be the exact same weights we used for the last image as well. These 3 weights are the weights that we're learning, or the perceptron is learning. These are what we'll call parameters or neuron weights or parameters of a model, not to be confused with the hyperparameters, which are sort of external to that. So this is parameters of a model we'll consider as weights as well, okay? And then likewise, when it's 0, 0, the value should come out as empty, so for our weights. Okay, so now typically, I would give out people a mat of that perceptron model and dice. And the dice, in this case, would have values from 0, a quarter, half, 3/4, 1, and 2. Okay? You can use either some pieces of paper that you write these values on, or some dice yourself. You only need about 3 pieces of paper. You can just keep writing different pieces of paper, tearing them up, or doing them in your really more meant to be done in your head. It's nice to have these sort of tools at hand, though. Okay. So remember, the value is, or the goal of this problem is to solve those three. They'll classify those three images. Now, normally we would start by rolling the weights, since we're using random dice. And normally you could just assume maybe just random numbers, or just assume any numbers that you want, just to try out something to start with. So we can do that, or another way we can do it is to use the perceptron update equation. So I don't typically introduce this because I know most people would probably just defer to this equation right away. So the reason I'm offering it here is this is really going to be more of a visual exercise, and people are going to be staring at the panel. So I want to give them another option here as well. So this essentially this equation tells us that the weight of 1, or the weight at time step 1, is equal to the weight at time step 0 times this alpha value, which is what we call the learning rate of the expected value minus actual value, the actual input itself. Okay, and I'll go over this equation again here shortly. Okay, so here's the equation. Is my bias. My predicted value is 4.
Hey, Michael. Jesse here. We just lost audio upon you clicking on this slide.
You lost audio on me?
That's correct. Yeah. Just on clicking on this, as soon as you clicked on the slide.
Oh, okay. Is it working now?
It is. Yep.
Okay. So let me go through this again. So the bias here. So this is the predicted values, and this is the way we're calculating it, right? So 1 times 2, 1 times 2, 1 times 2, 1 times 2, 0 times 1, 0 times 1. We add it all up, we get a predicted value of 4. We actually want a value of expected value of 0.5. Remember, that's the value we want to predict for this value. So that means our loss is negative 3.5, and we would need to push that loss back. Okay? That's using the update equation. You don't really need to do the update equation. Like I said, this problem is really about search, right? It's really about finding what those values are. If you want, I can go back to the original slide here. I think my next slide is the solution, so I can't. Yeah, let me just go back. Let's just take a few minutes and see if we can come up with the weights. The 3 weights. All we need is weight 1, weight 2, and weight 3. Just take a few minutes and see if you can think of the weights for those, what would balance those problems. Sorry guys, I just had to jump out. Did anybody have any questions or need any help?
So we're taking basically 111 and then timesing it by the numbers that you had on the dice, right?
Yeah. So remember though that you always want to use the bias, or maybe you don't have to use the bias. If you put a 0 here, that would cancel the bias.
Completely. Yeah.
Right. So then a 1 times a number plus its 1 times a number, right, equals 1. 1 times a number plus 0 times a number equals 0.5, and 0 times a number times 0 times a number equals 0. So as you can see, there's a number of ways for us to think about solving this problem. We can use, like I said, that update equation, or you could just randomly throw in values, or it really is just a search problem, right? We're just searching for those weights to solve it for those three images. Anybody think they're close? Is a gentleman that was in my deep learning workshop here? He should maybe be able to solve it quickly.
He's showing us the way right now.
Okay.
So Michael Aaron's got a guess of 0.5.5.
That is correct, yes. Okay, so let me just scroll through. So that is indeed the solution. So the solution for us would be 0, half, and a half. So you can work through that quickly. 1 times 0, 1 times 0 is 0, 1 times a half is a half, 1 times a half is a half gives us 1, 1 times a half is a half, 0 times a half is 0, gives us 0.5, and 0 times a half and 0 times a half, it all equals up to 0, right? And remember, we don't have an activation function in this case.
Mm-hmm. And that would cancel your bias because your first digit is your bias?
Your first number is always the bias. There's always going to be a bias in a typical simple perceptron anyways, okay? So there is another way for us to solve this, and this is the way deep learning networks actually solve this as well. We'll do a thing called batching. Batching allows us to feed in multiple images, and we'll do this in a number of different ways. And batching, because we're doing these things in tensor operations, or you can think of as a matrix operations, again, using GPUs and stuff like that, I simplified this just to say that we can average across images, expected outputs, and loss. But the same sort of mathematical approach happens when you're doing this with tensors, right? I'm not going to go into this too much, I'm not sure. But so we can do the same exact thing with the update equation if we batch things, okay? So we can batch things by taking this top value here, 2 out of 3 times is going to be a value of 2 out of 3 times, essentially, right? And then this bottom value, the 1, is going to be a 1 out of 3 times, right? So this gives us our fractions. We can use the update equations, again, for the values that I first use, using batching. So you can see here is my update with a loss, and then I calculate my new weights. So this is my new weights here. So this would be my first iteration of running a batch through. So I'm essentially training my model. I'm throwing these 3 images at it. I essentially average them, throw the weights, or throw the images at them. This goes through a training cycle of updating the weights, and then we go through and we see the next set. So these are our updated weights. Again, we throw the images at it, and we update the weights again. This time we get a value of 0, 0.75, and 0.5. Okay? And these values I'm rounding. I'm very much rounding all these values just to account that these are a quarter, 1, and a half. So these are the values. After 2 iterations, you can see I get a 0, 0.75, and 5. Which actually, for this model, turns out to be about the best we can do. Because I'm rounding off and stuff like that, it essentially turns out to be the best I can do. So the minimum amount of loss I can account for when I'm rounding things off is negative 0.17. A couple things to pay attention to, though, is the way that we're applying the learning rate. Okay, so notice how fastly our model is learning by using this 0.5 learning rate. Let's understand that if I used a 0.1 learning rate, we'd only essentially be doing an update of, say, 1 out of every 10 times. But when I'm using this half update, I'm essentially expecting my model to correct itself in almost one one iterate or one every 2 iterations essentially. This can be good and bad. In this case, it's good. I mean, it works out for us. You know, we can solve this problem in 2 simple batches. But if our learning rate is too high, we get lots of problems where the model just sort of starts to forget or just can't learn at all. Or conversely, if the learning rate's too low, the model won't learn at all, right? If this learning rate was really, really small, we'd have to throw a lot of different episodes, you know. In this case, we got away with 2 batches because our learning rate was 0.5. But that's one of the things we have to play with is this learning rate and loss. This is essentially how we train most models now, is taking or calculating this loss and then pushing that loss back. Okay, any questions about this? So in this example here, we would get in our problem, the solution with batching would give us these values, which are reasonably close. And we have a number of techniques we can use to round those off or better approximate those values, or at least sort of better define those values. Is there any questions so far about this before I go on to some other things? No? Good? Okay. Okay. And the way we do that is with activation functions. So there's a number of these activation functions that we can use and apply. And remember, the activation function is what we're applying here at the end of the model. Right here at the end of the model, it's the activation function. The reason why we apply that activation function is for a number of reasons. It's either to sort of balance out the model or constrain the model to some value. So in this case, if we used a sigmoid or a tan H, we'd essentially be constraining the values in this case between 0 and 1, in the sigmoid or in the tan H between -1 and 1. In a ReLU, for instance, we might just not want any 0 values, and then we just want to do a linear interpolation after that, or we do something like a leaky ReLU, or elastic, or I'm not even going to say that one. Okay, so essentially, we use these activation functions to constrain the outputs of our models, and we do that so that our models don't get too carried away, I guess sometimes you could say, or the weights or values within the models don't get so big that our model has problems sort of balancing them. That's a big reason for activation functions. It's a big reason for some other things like normalization, which we'll get to as well. And again, I'm just showing the math here just as a, just as an aside to say this is how it sort of works. Okay, we can also sort of talk about the step function. The step function can help us in that if we see values that are less than 1, we can count them as 1. If we see value that is just below 0, we just ignore it. So essentially, if a value is 0.5, it registers as 1. If it's 0.25, it registers as 1, etc. We can modify this step function. So we call it a half-step function. So that means that every value above 0.5 becomes a value of 1, and every value below 0.5 just doesn't make it through. Okay, so that's another useful step function as well. And as it turns out, that's a step function we'll apply in our next exercise. Okay, so in the case of our last exercise, if we apply activation functions, we can see here what's going to happen to each of our values when we apply an activation function. This would be the activation we apply right at the end of the perceptron to sort of balance out those inputs. And you can see here there's a sigmoid function sort of skews our middle value a little too much, so it's not really useful to use, say, the sigmoid function. The tan H function seems to be a better fit for this model, or the ReLU. Again, if we want to constrain to just a 1, that might be a bit of a thing, or the step function, which would give us some really unrealistic results, or the step half function, which might be in some cases more appropriate. So that gives you sort of some looks on why we might use different activation functions. Okay? So what we did essentially, or what we just covered, was what we call the forward pass. Now what we're going to talk about is the backward pass, or the way that our models learn. Now in most multi-layer perceptron models, using the update equation isn't applicable. We just can't use the update equation because each of the weights we need to tune or update really becomes complicated when we expand the model. So we expand the model to multiple layers with multiple perceptrons, we're assuming that each of these bubbles now is a perceptron. The calculations to perform to each of those weights becomes extremely complicated, to say the least. And this is where we start to see, so the forward pass we just done was really simple. The backward pass becomes really complicated, and that's where we introduce calculus, and where we start to do these partial differential equations, and we take their derivative with respect to the weights to find out how much each of the weights changes. It's essentially what we're doing, and we're calculating the gradient. So you'll hear this term gradient descent being used. Essentially, that's what we're doing, is just finding that value, that gradient that determines the amount and direction of travel that we should be decreasing that weight. Okay? So in the typical multi-layer perceptron, if you're going to train a model, it becomes really difficult because you can't use just a simple update equation. Okay? And here's another diagram. So I typically throw a bunch of these diagrams and just sort of look at or go with the crowd, but since I can't see you guys and what you're doing, I'm just going to assume that we're all good so far. So again, this is another example of how we run the back propagation. So in our update equation, we were essentially doing back propagation. We're pushing that error back. It just, when we get to multiple nodes in a network and multiple perceptrons, or what we typically call neurons now in a network, doing that sort of simple update equation over each of the nodes in the network becomes really complicated. And that's where we have to use calculus in this concept of gradient descent and back propagation. So essentially what we're doing is we're trying to find either global optimum or minimum. So in the case of gradient descent, we're often just trying to find the local minimum. And it's showing us global optimum because we'll often see the gradient is going up, but then we reverse the direction of the gradient and calculate it as going down. So internally, we'll see the gradient as a positive value, and then we reverse the gradient, sort of calculate and optimize the value so that we decrease the loss to 0. Remember that we always want to decrease our loss to as much as possible, right? And that decrease of loss essentially means that our model is trained better and better, right? Think of it as that update equation we're being applied across the network weights, okay? Now, there's various ways of doing this gradient descent and back propagation. There's a number of different optimizers we might use. The classic one that we would typically use is called gradient descent or stochastic gradient descent. And stochastic gradient descent essentially works by throwing multiple or random images like we just did in our example of batching, but instead of batching all images, it'll just pick maybe 10 images out of a batch of 1,000 and then just throw those images at the model and train those images. And then it just randomly does that over and over again. The reason we do that is so that we sort of get a better balance over the effect of each of those images that we're training through the model. Okay, so here again is the gradient descent and a couple slides on showing you how to do it. It's very mathematical. And here's a couple examples of various other essentially gradient descent based algorithms. There are variations of gradient descent that use things like momentum or just various ways of finding a better path to that local minimum in a diagram here. I've got a diagram here coming up. So here's a couple of examples where you have, two algorithms being applied to a similar problem. One might take this sort of longer, slower path, and one might sort of hop around and do something a little quicker. That's the same sort of concept we have with just using different optimizers. We never really have to look at or understand the sort of hopping of this and finding that global minimum, but you'll generally see that certain optimizers perform better than others based on how well they train and stuff like that. So the typical one we'll use nowadays, though, is Atom as an optimizer, but in some cases, some people you'll see using stochastic gradient descent or even gradient descent or other variations of different optimizers and stuff like that. Okay. And then there's other ways of finding the weights in a perceptron or a neuron. You could even use, for instance, genetic algorithms. Some people have used that, evolutionary search, particle swarm optimization slide, like I just mentioned, where they're using hash tables to essentially treat those, finding the weights as a search problem, which makes perfect sense. I mean, if so, Jesse, who solved the problem? Who was the one that gave us the answer?
I'm not sure.
Okay.
Yeah.
I was just going to ask if he used the update equation or he just.
Oh, sorry, Aaron Holmes did.
Yeah, if he used the update equation, if he actually just randomly guessed the numbers, or just sort of used his head to pick out the numbers too.
I used my head to pick out the numbers. Thanks.
Okay, great. So obviously, right? I mean, you can use either method. I mean, the reason we use sort of the update slow back propagation method is because it's the way that works for us. But there is probably better ways to find those weights depending on your approach and stuff like that. A big part of why these other algorithms don't perform very well is just because they're slower. But they weren't always so slow. So actually, genetic algorithms were used to train the weights in neural networks for quite some time, up and even to the early 2000s, I think. And even particle swarm optimization, I think, was used to train networks. The reason why they're not anymore is just because the number of weights we're training, and it's just faster on a GPU, and with the various deep learning frameworks we have out there and stuff like that, it just doesn't make sense. But that doesn't mean to say somebody else may not come back with another idea. There's so much research being done in these areas now. Okay. So if you want an excellent YouTube series that describes the mathematics and all of this stuff from the ground up, they give you a refresher, a lot of details in the mathematics. There's 4 series from 3 blue, 1 brown, 3 blue, 1 brown series, and an excellent series of 4 videos on deep learning and really go into the details of back propagation, right down to determining the indices of the weights and how you balance each of the weights in the network and stuff like that. So if you really want to figure that stuff out, then go there. Whoops, I did not mean to play that. There. Okay, so I'm just going to take a quick divergence from the perceptron just before we get into our first example, just to quickly talk about the way we do these computations in with perceptrons now. I mentioned a few times using GPUs and stuff like that. Typically what we do is this concept called the TensorFlow or computational graph. Hence the name tensor in almost every deep learning framework, or well, the ones from Google primarily. But tensor is very popular because it really is at the core of the mathematics we're using in these operations. So really all we're doing with the tensor operations is just essentially what we do in gamings, where in games you might sort of do these tensor operations or these matrix operations to develop shaders that give you a certain look, like some sort of great look in some video game, for instance. Well, that same sort of great look that gives us in video games gives us the ability to train deep learning networks, training all those weights and stuff like that, using these TensorFlow computational graphs. So in this example, or in this slide here, I've just sort of demonstrated the various types of tensors there's possible. So a tensor really could be anything. It could be a single scalar value to this simple 1D tensor. So a 0D tensor would be considered a single scalar. A 1D tensor would be considered just sort of an array of numbers. A 2D tensor would be a matrix. A 3D tensor, a cube. A 4D tensor is sort of a stack of cubes, and a 5D tensor is sort of a column of cubes, essentially. And then a 6D tensor would be a stack of cubes, essentially. Since we're all in IT, I think we can sort of appreciate that this really plays out to most matrix operations and the way we handle memory. It's really what most of this is about. And then the sort of the mathematic operations that go around it. When we sort of multiply tensors together, we get the benefit of being able to sort of simply do those matrix operations or those tensor operations in one single operation, where if we were to do them individually, each of those calculations could take some time, right? Okay. So in the case of TensorFlow. So when we sort of replicate this perceptron model, we're pushing it through, and this really becomes the equation. It simply becomes this Wx plus b equation that we can just wrap in tensor. That becomes a tensor equation. We have the tensor of weights times the tensor of inputs plus our bias. It really becomes a very simple equation when we do this with tensors. I just want to mention that. We aren't going to get to this level, guys, but I just want to mention some of the background and why we're using tensors. Tensors are pretty popular, or well, they're pretty dependent on everything we do in deep learning basically because we're just using these operations and facilities within the various deep learning frameworks and tensor frameworks to develop this stuff. Like I mentioned before, the tensor sort of mathematics is probably going to make its way into a lot more IT places, I think, in various, doing all sorts of mathematical operations, I would imagine. So we'll probably see this a lot more coming soon. Okay. I'm not going to go into that. So what I'm going to do is go into a simple example in Google Colab, which we can all walk through. Okay. And this simple example uses MNIS. So MNIS is a set of 60,000 handwritten digits on this 28 pixel image. It was sort of that one example image that I showed you earlier. This is the data set we're going to use to train a deep learning network to recognize each of the digits. Okay, so this is their problem. Just going to escape here. So to get to this problem, so if I could just get everybody to go to, let me just copy this and I'll put this in the chat. This is the GitHub page I have set up for this. Okay, and the one we're going to go into is the deep learning beginner. This one here. And at the top, there's a button that says Open in Colab. You want to click that. Okay. So for me, I usually typically, when I first come into these notebooks, is just to make sure what runtime I'm in. And so I might go on and look and say, okay, so I'm running a Python 3 and GPU. There is a possibility to run this as CPU using none, but I'm going to keep it as GPU because I just want to keep the performance. I should mention that, okay, so I'm using my regular, just a regular Google Colab account, but I do have a pro account as well that I'll sort of make a comparison on just to show you some differences in performance if anybody's interested in using Colab Pro. So I'm using Colab Pro in one example and one example not. So what I'm going to do is I just open this example and I'm going to say runtime. I check the runtime type and I'm going to say runtime run all. Now, when I click the runtime run all, it's going to connect the runtime. So right now you can see that I'm not actually connected. So it's not actually connected to a virtual machine that's going to be set up and run for me. And this all just sort of happens behind the scenes. But when I click run all, that's what's going to happen for me. And just say ignore because it was technically authored by the TensorFlow authors, but I've modified it somewhat. But I'm just going to keep the attribution there.
Jesse here. So you click on in the GitHub, there's the DLB _ beginner, IPNYB, and then after you've clicked on that, then there's a open in Colab button at the very top, and then you can just click on that button and it'll open it up.
Right. Yeah. Do we want me to show that again?
If you could, maybe. I didn't actually.
Okay. Yeah, because people might be. Yeah. Okay. So another way to find it is I usually just go my username CXBX MXCX Michael Lanham at GitHub, and then the repository is Calgary Deep Learning, and it's the DLB _ beginner. And the IPyNP stands for IPython Notebook or Jupyter Notebook. Essentially, it's IPython, but we all just call it Jupyter now. And then at the top, you'll see this button that says Open and Collab. It's a blue button. It's got the collab sign there, so I'm just going to click that. And that would take me to this piece here. So I've already got this running. I'm just letting it run. And then we'll just quickly go over the code. This is already running, so it'll be training as I'm going through, so we won't have to wait for it to train. But it doesn't take very long for this session to train. So if you want, just click Runtime Run All. If anybody's having troubles, just let me know. So again, here at the top is pretty standard imports that we would use for a simple example like this. Again, we're going to be using TensorFlow. In this case, version 2. 2 is just released late last fall, I guess it was. It was quite a change and allows for a lot of simpler execution. Normally, you have to build this computational graph, which was kind of a bit of an eyesore and a headache. So in this case, I usually print out the TensorFlow version so I can make sure that I'm running 2. Because some samples, even though 1.15 is quite new, some samples still won't run with the 1.15. So we want to make sure we're running 2.0, and we want to make sure that we're running in eager execution. So eager execution means that we don't have to set up a TensorFlow graph. And that's the reason why I mentioned that TensorFlow graph stuff in that. So eager execution means that all our blocks of code are going to run every time we run them. If you're not running eagerly, then you have to set up a session in the graph, and you have to run everything in a graph, and it just becomes not simple and not really conducive to a notebook. So we'll stay out of that. Okay, so most of these data sets are set up to really be easy to load data and populate your data set. So in TensorFlow, so what I've got here is I'm importing TensorFlow as TF. So this is the TensorFlow library. And from TensorFlow, I'm pulling Keras. Keras is another deep learning library from Francois Chollet. He developed in 2017, I believe. It's a sort of simplistic abstraction of what we would need to do for deep learning. And it really is sort of taken. We use a lot of those interfaces now to work with TensorFlow and build deep learning models, essentially. So you'll see a lot of Keras in here, but essentially consider TensorFlow and Keras to be almost the same thing. They've actually taken Keras in now as part of the TensorFlow framework. Question?
And NumPy is used to access data.
Yeah, so NumPy, the reason we use NumPy is just because tensors. NumPy is really good at working with tensors, allows us to reshape tensors and do some interesting stuff with tensors. Yeah, so that's the reason you'll see a lot of the NumPy stuff. So yeah, so this NumPy stuff here.
So the import really is just connecting this notebook, which is basically just like a Word document, to each of these different functions, and then you can actually run each function in the notebook and follow the progress of it in each section.
Right. Yes, exactly. Yes. Yeah, that's pretty much the Python Python Jupyter notebook yeah, concisely. So what we're doing here is we're going to first load and prepare the MNITS data set. So Keras comes with this data set sort of prepackaged. Again, this is automatically installed. We're not having to do any pre-installation of stuff on here. This is already just set up for us, and that becomes part of Collab. You might, in some examples, have to install some other stuff, and you could use like pip to install. If you're a Python person, you'll understand that. But what we're doing here is we're taking the MNITS, and the MNITS load data is bringing back a tuple of a data set that's giving us an X train, Y train, X test, and Y test. If you're a programmer, you may not be familiar somewhat with this, but this is just a way of bringing back essentially four variables in one function call. That's all. This is really popular to do in Python. So we're taking out an X train. X train means essentially our input data. X is our inputs, and Y is our expected values. So Y is in this case, going to be labels of 0 to 9. I'm going to actually write some class names here, just some helpful class names, so we can see what they are. But in these values, these Y train values, they really probably will only be, they will only be 0 to 9. And then the X test and Y test are again the same thing. And because we're doing sort of a deep learning exercise, we always want to test our data, or we always want to test our model to make sure the validity of our model isn't being skewed by unknown random factors. So for instance, our model, we could be actually maybe taking the top 40,000, so the reason we do this here is we're splitting our data set into a train and test set. Typically, we'll split our data set between 80% training and 20% test. That's the typical data science rule, essentially. The reason we do that is so we can validate our model after we train it. This is pretty important because, like I said, if you consider, for example, if we take our whole training set includes all the digits except for the digit 9, we would not be able to determine that until we've done a test. And the only way we can make sure and get these tests correctly is if we do a sort of a random enough batching and stuff like this. But for this case, we're just going to take just the raw values that we get from here, just to keep it simple. Now for here, what I'm doing with this X-train and X-test, now X-train represents the images and X-test represent the images. So remember, the X represents the images of 784 values in both these, and the Y-train is going to be a value of 10 values that represent our output. Now I say 10 because instead of just saying a value from 0 to 9, it's actually better that we classify our value using what we call hotkey encoding. So in hotkey encoding, if we had an array of 10 zeros, for instance, and we wanted to represent the number 9, which is the 9 is the top value, for the top value in that array of 10 values or array of 10 zeros, we would put a 1 in. And that would be a hot-coded in value for 9. Likewise, if we wanted to hot-code in a value of 0, because 0 is the first digit, we would actually enter a 1 in the first spot of our 10 zeros. So we would have a 1 in that first spot. So that would be a hot encoded of 0. Okay.
So deep learning loves Boolean values, and a Boolean, for those that don't know, is a yes or no, a 1 or a 0. So if you can feed data in saying either it is or it isn't, then it's a lot easier for a logarithm to figure out to predict what the values are, or to build the model correctly so it'll identify them. Is that fair?
Well, again, it depends on the model. So in this model, that could be a fair assumption, because we really want to predict if it's a 9 or not a 9, and then we don't want to predict what other numbers are. And I'll show you how we sort of can classify that stuff using that one hot encoding. But before I get to that, so the next line here, the reason why we're dividing by 255, if I go back to that original slide, remember our values in the image were from 0 to 255 on a grayscale. But in deep learning and in any sort of regular machine learning exercise, it's usually better to keep our values closer to 0. So we'll often keep our values either from the range of -1 to 1 or from 0 to 1. The reason we do that is just to sort of normalize those values. We don't get those scary values. We don't get large values. Anytime we have really small values or really large values, that becomes a problem for balancing those rates. Just remember that. Remember that if we're getting huge values, that means our weights are going to start to become really big and unmanly, right? So we want to keep things within the 0 to 1 range. That's a real big reason for doing that. The next one here is just a simple, I'm setting class names to this array, so that's all this is. And then I'm just importing math, in this case, math library, and I'm just using that to determine a ceiling. In this case here, I'm just determining the layout of the images, so just the grid itself. So not so much for this. And this is a function here called plot data. It's going to take the number of images I want to display, the images and the labels. Okay, the labels here with the class names. So down here, I'm going to call that plot data function with 25 images with my X train set and my Y train. Now these two data sets should be lined up. So a value from X train of 5 should represent a value from Y train of 5, and that's what it's telling me. So I'm just confirming that my X train and Y train are all lining up, just to make sure all these things. And this will give you an example of what this data set actually looks like. These are all the handwritten digits and This is the way they're classified. So, and that's what we want to classify. So when we see something like this, we want to tell the deep learning network, well, that should be a 1. Okay? So that's what we're training our network on. Okay. So the next thing here is we're building our model. So in this case, I'm building a sequential model, and that means I'm just building sort of a stack model. And this is the typical model that I've already shown you a number of times, where you see a stack of neurons at the start, and then a smaller set, and so on until we get down to our output. So in this case, remember, I'm flattening our images, and our input shape is a 28 by 28, but the output of this is going to be 784 inputs, right? And those 784 inputs are going to go into my dense layer of neurons here of 128 neurons. So I'm going to have 784 weights or parameters times each of these neurons, plus 1 for our bias. And I'll confirm that in a second here for you guys. And then the activation function is a ReLU. And a ReLU function, again, is just sort of like a line with then a linear function. And then in this case, we're going to use dropout. I won't talk about this quite yet, but then we'll get into a standard dense layer of 10. And the reason we're using 10 here, again, is because we're one-hot encoding all our values. And by one-hot encoding, so each of these neurons then can learn which digit it needs to represent. So that's the benefit. So, for instance, our 9th neuron would need to learn how to sort of classify what a 9 neuron or what a 9 image looks like, essentially. Okay? And then we can do our predictions. So this is just looking at what those predictions are. So what I'm doing here is I'm just doing a quick prediction of the model. So I'm calling the model with one of the values and seeing what the values come back at. So these are the values that are coming back from an untrained model. And they don't mean a lot, and they really shouldn't mean a lot, because our untrained model should just be trained with, or just be set with random weights right now. Okay. What I can do here, though, is I can say if I want to take a closer look at my model. I don't think I have anything. Oh, here. So after the model is compiled, let me just go back. I'll go back up here because I want to cover this stuff as well. But I just want to go back, and I'm just going to show you what the model looks like. So I'm just going to go and type out model.summary. And you can see I have some IntelliSense as well here. And it's showing me what sort of options I have. You can see that I have some options here as well. So it gives me some helpers. And I can just hit tab and it'll finish for me. And I'm just going to do a simple blank model summary.
This is one of the benefits of these Jupyter framework, is that it does pop up words, so that it'll actually suggest what you should need to type versus you needing to remember all the different syntax and whatnot. It's like basically spell check or grammar check.
Yeah. Anybody familiar with C# IDE or Visual Studio would be very helpful. Very happy with this. Okay, so I'm just going to run this just to see what our model looks like. So remember, we're flattening it to 784, and then I'm pushing that through to a dense layer that has 128 neurons, but remember that's 784 inputs into each neuron, which gives me over 100,000 weights. So remember, this is just one layer has 100,000 weights over these 128 neurons. And then our last layer here is 128 coming down to our dense, and it has 1,290 parameters. So we can see that we can get the 1290 because we're taking this 128, we're multiplying it by 10 for our neurons, so that's 1280, plus we have to add 1 for each bias, right? So when we add 1 for each bias, that gives us that 10 extra, and that gives us, for that last layer, 1290 weights. If I was to do the same math, I would come up with the same number for this 100,000 or something here as well. So everybody sort of got that? So remember, this is a 2-layer model, and we're already over 100,000 weights just for this simple MNIST problem. So this is another reason why it's taken deep learning so long, because this can take a while to train. I mean, if we were just using a CPU, it takes a few minutes. With a GPU, it's much faster. Okay? So let me go back up here, and we'll talk about model predictions and stuff like that. So this is the output of the model itself right now. Remember, this output isn't going to make a lot of sense because, well, it shouldn't. I mean, our model should just be set by random values, okay, at this point in the notebook anyways. What we do, though, is we apply a softmax function against our predictions, and then this numpy operation here just means I'm turning it back into a tensor. So this is just essentially just a helper method for reverting this into a tensor, so it's something we can look at, a little helper. So we're taking these values here that are all some random range of values, and we're essentially putting them on a scale that is sort of from 0 to 1. It's sort of, you can think of it almost like a percentage value. So you'll see that likely the most likely value here, I guess, I would say is this value here. So if I had to say our prediction for our model would have been this value. It would have been suggesting, say, for instance, a 0, 1, 2, 3, 4. So for that number, it would have predicted a 4. If that was wrong, then we just would have taken that and subtracted the numbers from this and pushed the loss back. The thing is, you don't have to worry about these sort of minute details because this happens all internally in the model, more or less. I'm just sort of defining what this softmax function does. Okay, so you can think of it as it's taking these values and putting them on a scale between 0 and 1, all around each other, sort of normalized to each other, you could say. Okay, and then what we do is we apply our loss function, and that sparse catechol cross entropy is essentially taking a cross entropy operation against these values to determine how much the value is out. So if, for instance, if our number was actually a 5, we would say, well, this needs to be applied some loss, and likewise, these values also need to apply some loss as well, right? So that's essentially what the sparse catechol cross entropy is. From logics, meaning it's just being applied from these values. Again, there's lots of examples of using this type of stuff. You'll be able to see these types of equations and stuff like that used a lot. In most cases, we've actually sort of defined the loss function separately, but I think in some cases we'll actually even only say the name of the loss function we're using in the model. Okay, I wanted to define this here because many people ask me what does that sort of mean. I don't know if I really gave it a good explanation, or it's often probably better in front of a whiteboard. Anyhow, okay, so here you can see this is the loss function, and this is the amount of loss that's being calculated from our prediction. So from our last prediction, which was so bad, we see our loss here is 2.57, right? And that's the loss that's being applied back. So, and this is the way the model is being applied. In this case here, we have an optimizer, which is Atom. Remember, that's that stochastic gradient descent sort of modified version. Atom is essentially a derivative of stochastic gradient descent with momentum, essentially. You can see our loss and our loss function. In some cases, you might even say loss equals mean squared error, or loss is categorical cross entropy. You might only name the loss function here, for instance. In this case, we've identified this loss function, but in most cases, you won't even have to identify the loss function like this. But this gives you some control over how you can define the loss function or specialized loss function if you're doing something specialized. And then the metrics, I'll get into more metrics later, but metrics in this case is accuracy, so how well essentially it's putting or picking that value in the proper bin. So if this was a 5, for instance, how well it sort of put it within a 5. In this case, let's say it was pretty poor, right? We might have a low percentage of accuracy, whereas when it starts to identify it as a 5, how well is it identifying as a 5, essentially, is what that accuracy number tells us. Okay. Here again is our summary, and then here I am training the model. So this is just a very simple line I just ran. Okay, I'll run it again. On a GPU, it shouldn't take very long. So you can see here, this is its training. It's training on 60,000 samples. You can see even after the first iteration, again, I'm pushing all 60,000 samples again through. I'm not pushing all 60,000 samples through the network at the same time. What you're seeing through here is each of the batches of the samples getting pushed through. So each tick on that little bar is a representative of the batch we're pushing through the network. Okay, and you can see this is the amount of time it's telling us how much it's training per sample, and then the accuracy. And we can see the accuracy is going up quite well. Remember, this is only accuracy against our training, right? We're not doing any accuracy against our test, so we don't really have a good idea how our test is working yet. And then we can evaluate on our test here, and this is where we're evaluating, and we evaluate on our whole test set and our whole test set using an option of verbose 2 here, and this is just giving a simple example of what it's evaluated after the calculating using our test set, which was 10,000 images. And you can see we're getting an accuracy value of 97.8, which isn't too bad. It's somewhere around there, right? Okay. And then we, some function code here to plot the predictions. I'm going to randomly pick a range here of 25 images somewhere in the set and run predictions. And you can see, I think the predictions will generally be pretty good. You might see one of these numbers being out on your side. For instance, maybe 1 being out. If I run this cell again, I can see it'll just do another random pick. Yeah. So it's pretty accurate for the most part, considering we've been able to train this over 5 iterations pretty quickly. Okay.
How many iterations would you typically run this on? I guess it depends on what level of accuracy you want.
Yeah, absolutely. Depends on your data, your accuracy, and stuff like that. And we'll definitely get into that as we go into other more advanced deep learning models. Yeah. Okay. So any questions on the MNIST, guys? And I just have a test here. So what I just want to talk about here is just some functions, loss functions. So again, in a typical model, we might actually define that last exercise like this. I broke out the last 2 steps there so we could identify or understand the activation of softmax on the last piece and that loss of sparse categorical cross entropy. But in most cases, the model could be defined simply as this. We wouldn't have to define a special activation function or a special loss function. We could just use the name functions, right? And there's a number of these different name functions that you can look at. Softmax, sparse categorical cross entropy, or regression, or other different methods you might use to analyze your problem. We'll typically use softmax, sparse categorical cross entropy for classification problems. We'll use ReLU maybe, or something else for regression problems. It really depends on the problem you're looking at. Okay. And again, this is sort of a diagram of what I talked about in the thing there. Of we're essentially doing the logits. That's what should be given as logits. We're applying a softmax function that gives us that one-hot encoding labels that we're wanting to spew out to the network and as our answer. So that's essentially what we're doing in that operation here. Okay. Any questions with that, guys? No? Okay. And there's a number of different metrics we can apply to deep learning models. We'll get into some, but stuff like mean squared error if we're doing regression, other types of classification as well. And other types, right? And unsupervised stuff as well. And we'll start to look at that here, unsupervised here in a second. Okay, so here's an example of supervised learning with regression or classification. So on the one side, we see they're performing regression. We're essentially trying to fit a line to our data or fit a function to our data.
Can you explain, Mike, the supervised learning versus unsupervised?
So supervised learning is pretty much what we just did there. So we're labeling an X set and a Y set. So we're defining what the output should be. We know what the expected output should be. That's what we typically refer to as supervised. That we have labels on our data, and then we want to train our model to those labels. Unsupervised learning is where we might know an answer, but we want the model to find the answer on its own. That's the most open way I can define it, because it itself is becoming a little redefined lately with some of the models and what we're doing. you can almost say in some ways we do a lot more what I'd like to call semi-supervised learning, where we're sort of helping the model along a bit, and we're giving it directions and telling it what it could do, and not so much unsupervised learning. So unsupervised learning, I would say, would be entirely, it's just learning the environment based on some internal rewards or internal motivation or stuff like that. And that's would really be unsupervised learning. But that sort of goes into some of my learnings of reinforcement learning and stuff like that. So we won't get into that. But yeah, so we'll look at supervised learning, we'll look at unsupervised learning, or what some people are calling adversarial learning, but we'll get to that in a bit after our next section here. So before we jump into a couple other things, what we could do now is to jump into, I realized I just flipped my slides again, TensorFlow Playground. So I really don't need to, but what I'll do is I'm just going to go to, like I said, there's all these names with tensor in them, and I got to pick what page I got to go to here correctly. So here I've gone to a site called TensorFlow Playground, and you can find it by just Googling TensorFlow Playground, okay, and it should be accessible. Not TensorSpace. We'll get to TensorSpace in a second. But TensorFlow Playground. And this allows you to play with a deep learning network. It allows you to change the number of neurons, number of layers, the number of output neurons, the type of problem you're doing, and it shows you a number of things about options that you can change and modify. So you can see the values of x1 and x2 are sort of like distributions of values. You can think of range of values, I guess you could say, that are coming into our model. Our model then is our neurons and an output neuron. You can see I could add an output neuron. It's sort of giving me a different classification piece. If I run it just using this, you can see it's giving me those two curves there. And I'm going to stop it and run it again so we can see. So yeah, let me just change something in the model, I think. There, I have to change something before I can, okay. So I'm going to run it. Oh, that wasn't good. Here. I'm going to make the model unwieldy. Now, one of the reasons why I often like to show this is because a lot of people or a lot of newcomers think that the easy way to build their model is just add a whole bunch of neurons and add a whole bunch of layers and so on. So let me just show you what's going to happen if I add a whole bunch of layers and so forth. So I've added a whole bunch of layers, neurons. Now you can think of each of these boxes here as being a perceptron, that model we just looked at. So the inputs are all coming into it, and then it feeds out a single value based on whatever the activation function. And we can change the activation function up here. We can modify that. I'm going to choose, for instance, a ReLU. Okay. A linear activation function means essentially there's no activation function. It's just letting the value out as it is. Okay. Regularization essentially means how we regularize or normalize the values, and I'll get into why we might do that, but that's often very useful because, again, we don't want those values getting too big or too small, right? Okay. And then the regularization rate is just determining how aggressive we are at regularizing, et cetera. And for this problem, I'm just going to keep it classification. I'm going to keep it 2 inputs, and I'm going to let the model expand to this huge amount, and I'm going to train it. Okay. You can see it doesn't do a bad job. What I'm trying to do is sort of break the model here. What I want to do is, by adding more neurons, you can actually cause the model to what we refer to as overfitting, or underfitting in some cases. But what I can see, so what I'm looking at here is I'm looking at these 2 lines, and there is actually 2 lines there. What I'm trying to do, though, is not get them there. Let me just take out, and feel free to play around with this, guys, as you're watching me play around with this. Okay, I'm going to do this at 2 and 2 and see how this works. Okay. You see these 2 lines here. The one line represents our test, and the other represents our training. The darker line represents our training, and the lower line represents our test. So we always want these two lines, and that represents lost, right? So we always want the loss to converge to 0. We always want the loss to converge to 0 with the same values. And the reason we want that is because we want to make sure our training set is being trained on a representative sample of our test set, right? If it's not, then as good as our model could get to 99%, it could still be garbage, right? That's an important thing to remember, is that we always want to make sure and validate our test, our model against test. And some people might actually do a test validation set and then actually validation set that's separate, that they'll never show to the model. And the important thing is you don't show the test set to the model. That's another important thing, because you don't want to vary the model at all. So you often want to keep this test set isolated until you need to train it on the model. And some people may not even train their validation set on the model until right at the very end, just to see if indeed their validation is confirmed. So they would keep that validation set completely separate and then train it on that validation set. And if it didn't work well in the validation set, they throw the model out. And that's the way it has to be sometimes. I mean, the model has to be representative, or has to be within those limits you expect it to be. Okay? So let me just... Okay. What I'm going to do here is just pull the screen over, because I don't need to go through all the slides. And feel free, you guys feel free to the slides if you want them as well. Okay. And so the reason why we often want to worry about how much a model is adhering to carrying that loss through. So if I go back here, so the amount of loss that's getting carried through, as I expand the model and deepen the model, that can get out of hand, right? It can either get too big or too small. And that can either carry itself about as underfitting or overfitting, or what we call exploding or vanishing gradients. And what happens is that the weights, or the sort of gradients that we're applying or trying to apply to the weights, either become so large or so small that they've just become useless, right? They just so widely vary the model that the model becomes useless and unable to learn. So that's the reason why we often want to make sure and limit the size of our model for one reason, but that's the reason why we might want to enter regularization, or what we call normalization, into the model. Essentially, what we introduce here is regularization or normalization between each of the layers as a way of rebalancing those weights, or renormalizing those weights. So the piece we've seen at the start of the model when we enter the inputs, where we regularize the values by dividing them by 255, is the same thing, same sort of operation we might apply between layers. This is sort of regularization as well. Okay. Now the reason why I just wanted to jump around on here is because I have another test coming up as well. So, and a lot of this comes down to over and under fitting. You can over and under fit a model by adding more neurons than you should. For instance, if you add so many neurons to your model, what can often happen is your model can essentially learn or remember the data. It remembers the data so well that you can see we got from the GAN, for instance, where it can just regurgitate out what it just learned, which is in some cases really good, and in some cases not so good. So that's the thing we have to be aware of as well, as over and under fitting. Okay, and then the things I talked about as far as fixing deep learning issues. So the overfitting is the network size and dropout. Underfitting, again, is network size. And then vanishing or exploding gradients is we can rectify with normalization, or we can just make sure and march our range and stuff like that. And then just a quick discussion about parameters and hyperparameters. So parameters are the weights that we train within the model. Hyperparameters are the types of parameters we might use. So used to train those parameters. So it could be the number of epochs we're using. It could be the momentum, or the amount of aggression we want to do for normalization, for instance, or the amount of momentum we want to apply on our gradient descent, for instance. Those are all the types of hyperparameters. other examples of hyperparameters might be the number of layers of the neurons we're using in the model, or the learning rate, for instance, right? Those are all types of hyperparameters, and the parameters are the weights themselves, okay? So just some summary. Here we have our input layer, right? An activation function that gets applied to that pushes those values to the next layer, another activation function, and then so on. In between here, there could be some normalization as well to sort of normalize those weights. We might often do that. And we'll look at some more examples of this as well, guys. Okay? Any questions? And then I have another quiz. We'll probably just take a few minutes on. I just need a quick break.
So do you want to take 10 minutes or 15 minutes, Michael, or?
Yeah, let's just do, this one's a little longer, so we'll take, about 10, I guess.
Sounds good. Okay, so we'll be back at 10:47.
Okay, thank you.
Thanks so much.
I put these tests together, and I think I normally have an agenda. I've changed some of the content in the course, but hopefully the test still plays. And most of the items in the test here really wanted to teach you guys anyways, is sort of the basics or fundamentals. So really, what was the biological cell that was the inspiration for the deep learning research? So that was a neuron. Again, that was what sort of inspired this whole journey. So how many weights does a perceptron with 5 inputs have? So remember that we always need to make sure and count the bias so that we have 6 weights. Okay. What is the output from the pictured perceptron, assuming a linear no activation function? Okay. So the answer for this one is 14. Again, 1 times 3, 2 times 2, 5 times 1, and then let's not forget the bias, 1 times 2. All the total is 14. And again, the same type of question here, just so that you reinforce those values. And this answer for this one is 19. And again, another time. This time it's a little different inputs. And the value is 1, since we're using a step function. So in this case, we're using a step activation function as shown. And this activation function should be 0 to 1, is what was shown there. So that was the trick in this exercise. So just being able to do that at 1 value. Okay, and what is the activation shown below? We just briefly covered that. That's the ReLU activation function, so that first one. Okay, and select the letter of the graph that represents a sigmoid activation function. Well, this one looks like it's backwards. So that one is D, should be D. And select the name of the method used to train loss back through the network, and that's back propagation, not to be used with forward propagation, which is what they call the forward pass through a network. And select all the function types used in a deep learning network. So all the first 3 are good, but the last one, globalization, we don't really use anything called globalization in deep learning. Okay. What is the purpose of loss function used in a deep learning model? And it's used to calculate the amount of error in the forward pass. So essentially how much we are out from our expectation in a supervised learning problem, essentially. Okay. Select all the methods that are optimizers. So ATOM, SGD, which stands for stochastic gradient descent, mini batch stochastic gradient descent, all 3 are correct. And then these last ones, this one here, ReLU, is an activation function, ELU is an activation function, MSV is a type of loss, essentially mean squared error, and GAN is a generative adversarial network. Okay. What are the activation functions and the order they are being used in the example below? So the activation function in this line is ReLU, and the activation function in this line is softmax. So this answer here, ReLU and softmax. Okay. What is the optimization function being used in the sample below? You can see here the optimizer being used is ATOM. So the answer here is ATOM. Okay. So I didn't really get into this too much, but between gradient descent and stochastic gradient descent is stochastic gradient descent is random. Stochastic essentially means random, so it's essentially applying that random process. gradient descent is essentially working through batches of images, but with no randomization. So it suffers from, cyclic training essentially, where stochastic gradient descent doesn't suffer from the cyclic values. Okay. The network below is compiled to what type of DL problem? So is this a classification or regression problem? So this example here, again, is a classification problem, something we'd want to class. The output of this is probably going to be some one-hot encoded values or set of values, for instance. Okay. And what type of metric is used in the model below? Accuracy. So again, we're using accuracy in this model. Okay. Select the letter of the image that represents the 4D tensor. And again, that's image B. Right? So this, that's a 5D tensor. Image A is a 4D tensor. Image C is a 3D tensor. Okay. What is considered the classic data science train and test split percentage? And that's typically 80-20 is what we follow. And what name do we typically use to identify logistic regression as regression with classes? And that's, again, classification. So essentially, in all of our models, we are really just doing a regression problem. We're just finding numbers. But in logistic regression or classification, that's where we're sort of dividing or using that line to separate one half of the numbers from the other half. And what do we call the middle layers in a deep learning network? And that's what we call hidden layers. Okay, you'll often see that. I didn't cover that, sorry guys. And select all the variables that we classified as hyperparameters for a model. Okay? Number of layers, learning rate, the number of neurons, and the weights in the network is not something that you would have the ability to change. This is really going to be an after effect of determining the number of layers and number of neurons, for instance. Okay. Any questions on that? No? Okay. So let me return. So the next piece, I want to just jump quickly back into another code example where we're looking this time at a more difficult data set. And this is the same sort of provider of data, but this time we're looking at the MNIST fashion data sets, which is essentially a set of images that show 10 different classes of apparel, essentially apparel that you'd wear. And I'm just going to quickly go through this quickly because we're running out of time here. We might have to shortcut a few samples. So again, this is just the input piece. In this here, we're defining some constants that just define our training buffer size and our testing buffer size. So we're just doing a 60,000, 10,000 split. This is the dimensions of our image. It's 28 by 28. And this 1 represents the channels, meaning it's just a single channel. Okay. And then from here, this is just loading the data from the MNIST data set. And we load it, again, using just a different helper. So before we were using MNIST, now we're using fashion MNIST, and we're just calling that load data. We're again we just need to reshape that data a little bit into a 28 by 28 by 1 channel, and then we're normalizing it again by dividing by 255. And then we define our class names. Again, this is the class names are defined based on the classes. So it's t-shirt top is class 0 and class 9 is ankle boot. Okay, again, same code here to plot our data. I'm just going to plot 25 images from that same set, and you can see it's the same thing we did from the last example, same sort of output, so you can see all the different things and what you should expect. So there's a sandal and what it sort of identifies as a sandal. So this time, we're just going to be training our model to identify these apparel items, right? So we're going to essentially build the same model. I'm again building this time input shape 28 by 28 by 1 channel. It's dense. It's essentially the exact same model. I'm going to do a simple prediction. I'm going to output the model itself. So again, it's exactly the same model we used last time. Here's that other stuff, and then we're compiling the model again using that loss function and the optimizer, training it, and this time we only get about 88% accuracy. Now, a big problem with this, and we can see our predictions, and you can see there's probably a few more that are wrong in this set this time when we run through this model. But one thing we can see here is that our accuracy drops off quite a bit to a problem that doesn't seem to be that much more difficult to us. So what's going on here? Why is the model having so much troubles? Let me just jump back into the PowerPoint. Okay. So like I said, the model just starts to degrade quickly. It just attains a maximum accuracy of about 87%, which is not really valuable because it's essentially 1 out of 10, or 1/10 of our classes are not going to be classified correctly, which is not very effective. So in order to do better, one of the catalysts that I mentioned before was this work by Hinton in developing this thing called convolutional neural networks. Now, convolutional neural networks work by clustering features of an image together. It's kind of similar to the way our own eyes function, is the way they've discovered, is that we have these sort of, these cornea, I guess, that pick up or identify these features, that cluster them into these sort of patches that we identify in our brains. And this is sort of the work Hinton had done, is developing this convolutional neural network system. And this is the system that essentially increased the percentage rates on the deep learning models above the classical machine learning models. This is the edge that sort of broke a bunch of the deep learning walls that faced. It was a challenge in 2012 that Hinton's team built AlexNet to classify the 1,000 classes of images in ImageNet with their convolutional neural networks, a couple percentage points higher, actually. So it was quite a turning point in deep learning. So what we see here is, in a convolutional neural network here, what we have is a convolutional layer that separates the image essentially into its features, and it does that by learning filters. It learns these filters that extract images, or filtered images essentially, that then it uses this pooling operation to sort of collect these filters, applies another layer of convolution, and then applies them again, and then it flattens the image. So the big difference here as well is that before we were always just flattening the image, right? We just took this image, we flattened it to a vector of 784, and then we just pushed it into the network. We didn't really have any semblance of what features were important to other features. We had no sort of correlation between what features might be more important to other features. And that's where the convolution comes in. Convolution essentially learns the filters to be applied to the image to extract those features. So let's see how it works. Okay, so what essentially it does is it passes this filter across the image that then extracts the features that it wants to train on later. The weights, the values that are learned are these weights here in the filters. So you see the -1 and the zeros and stuff like that. Those are the weights or the parameters the network is actually learning. Those are the filter values the network is learning in this case. It's essentially learning how to filter across the image. What it's doing here is essentially convolving across the image in a kernel patch, what we call this patch that's getting passed across the image, a kernel. In this case would be defined by 3 by 3, since it's 3 by 3. And it's being ran across the image by a stride of 1. I mean, it's only going across the image one pixel at a time, essentially, which gives us this output. Okay, you can see in the resulting image is 1 pixel less, and that's typically what happens unless we apply some sort of padding, meaning we take or want to use some sort of blank outside of the image itself. Okay. So here's another example of how it works and how the convolution works and it's being passed across an image. Now remember that the filter here is the part that's getting learned. The network doesn't care about the image itself or the size. It's not learning the size of the kernel. It's not learning how much stride it should carry across. Those are essentially hyperparameters that we need to change. What the network is learning, though, is the filters themselves. So So in this example here, this is an example of original with a filter being applied, and then this other filter being applied with a smooth. And you can see the result is the operation of two filters being applied to this image, what we get. It's essentially what the machine or the model is doing is extracting either edges or features using these filters it learns on its own to make. Okay. A really good example of this is a site called TensorSpace Playground. Not TensorFlow Playground, TensorSpace Playground. So we can go to that. In TensorSpace Playground, so here's an example. I have AlexNet loaded. So when you go, I'm not going to go back, but when you load up TensorSpace, here, I'll just go to the page here quick. I usually just type TensorSpace Playground, type that, click on Google, and it'll start with this sort of interface here, allowing me to pick a number of different models. So the model I've loaded is AlexNet. This model can take a little while to load. It is a little larger. It is 237 megabytes, but it's the one I'm looking at. It's the one that Hinton's team sort of built on the ImageNet challenge. So let me just go back and we'll examine the AlexNet model. So this is the model we're looking at is AlexNet. So AlexNet is what we consider a three-channel model. So in three-channel models, we essentially break the image up into its component channels, red, green, and blue. The filters are getting applied across each of those channels and extracting the features it needs. Now here's a result of the operation of these filters. Now when I click this yellow square, this is a convolutional layer, and when I click it, you can see the result of those images. Now remember, this is not the filters themselves. This is the result of the filters being applied to those images. This is what the machine is learning to extract from the image. What the machine, I'm calling machine or brain, is learning to extract. So you can see it's learning to extract features at this stage looks very much like a dog, or large pieces of a dog. And at this first layer of convolution, we're really only extracting the higher level features you can think of, right? And then let me just it is a little tricky to drive this. So the next layer is a pooling layer. You can see this is where all these inputs are going into my pooling layer. And this is where the images are essentially getting all collated together into common features. We apply either a max pooling or average pooling across the images to sort of collect all the features that were sort of extracted from the convolution themselves. And then from that, we enter various other convolutional layers. So each of these yellow boxes represents a convolutional layer. Notice how we don't always apply pooling on every convolutional layer. So if you want to see, we can actually go down to, say, the last convolutional layer, and I can expand that and zoom in to see what sort of features are getting learned to identify a dog. So let me go, whoops. Sorry, hopefully I'm not making anybody sick. So you can see as I zoom in on the image, that's essentially the level of features. So at this stage, it doesn't really look much to us. This is at the base level some of the features that are getting fed on the model. Okay, these pieces are all getting fed into the model. Let me just zoom out. And I'm just going to turn. Okay, so what we have here is, so at this stage, we see this green line. I'm back away quite a ways because this is going to expand. This is where we're flattening the model. Remember, this is the part where we need to flatten the model into sort of a vector of numbers that we input. And then when I open this, so I just clicked on that. We're trying to click on it. There. So you can see it's expanded quite a bit. And this represents the huge number of inputs going into our next layer. So you can see that's all those values going into what we looked at before already is our, and then this is just a normal layer. And then this is our output layer. So this last part essentially is just a normal neural network. The first part is all our convolutional layers. This stage here is where we flatten everything and then push it through the rest of the network. And this last piece is our classification. Now remember, we have 1,000 neurons here because we have 1,000 classes in our one-hot encoding, right? The ImageNet has 1,000 classes, so we're classifying 1,000 classes in this example. This really gives you a good example of what or how convolution works and how those features looks like. So this is a good one to play with if you want to understand convolution a little better. Any questions, guys? No? Okay. So let's go into the fashion DLB underscore fashion underscore CNN example. And this is an upgraded example from what, and we could apply this same sort of use of CNN layers in the MNIST example, but it's more dramatic in this example here. So what I've done is pretty much almost the exact same example. The only thing I've done here is I've added a convolutional layer and a padding layer. Okay. So what we're doing here is I'm adding, the output is 64 filters or filtered images, and I want to pass a 3x3 kernel of one stride. The default is one stride. It's just going to use one stride, and this padding is the same, meaning we're not going to pad it, so our images are actually going to go down in size a bit. Not details you have to worry about unless you're really getting into building convolutional models and that sort of thing. Okay, the important thing to realize is this convolutional layer here is helping us to extract features of the model. Okay, so when I go down, and you can see now our model is sort of expanded. Here's our convolutional layer. It's only 640 weights. Again, there's, so 3x3 represents 10 weights. Remember, we have a bias as well. So 10 weights for each times 10 gives us our 640 weights in our first layer for our convolution. So remember, it's the weights we're learning, not actually the output images. And then those get fed into this dense layer, and you can see now we've got 160,000, sorry, a million. Sorry, that's a million. So we have 1 million neurons, or 1.5 million neurons in our first layer, into our first layer after we flatten. Remember, this is the flatten operation here. Again, this is all the same, but now I'm going to train the model for a little longer, and you can see the accuracy we can attain over 91%. It's not likely we would attain higher accuracy. We can attain higher accuracy by adding more convolutional layers. I'll leave that up to you guys if you want to do that. I do have a couple other examples, but we're going to go through some other stuff here pretty quickly. I just want to get into some adversarial stuff and get into GANs at least. So, and here you can see as I go through, I've added some history stuff in this example. I'm plotting the history, and you can see I'm plotting the validation accuracy, so essentially our test accuracy against our training accuracy, and we get a divergence here. So you can see in our model, even adding that one convolution, although we're getting a good training accuracy, our test accuracy is falling off. So, you know, we wouldn't really consider our model that valid, but there's a way to fix that. And we can fix that with adding a dropout layer. And we can show you how to do that quickly. I'm going through this a little quicker right now, guys, because I just want to jump to the last game and then hopefully one other sample. So here I've got another example here where I've gone a little crazy with other layers in the model. We'll just show you this quick. I'm just going to run it all. I don't know if I'll have enough time to look at the output. Okay, so here you can see I've gone a little crazy with the model. So this is the model now that I've built for this problem. You can see I've added convolution with different filter sizes at the top. I've added this thing called batch normalization. That's essentially to prevent that exploding or vanishing gradient problem that we can see, or getting too many hotspots. For instance, if we train a whole bunch of 9s together in a set of images, we might get some hotspots over the 9 area. We want to avoid those hotspots, right? So that's where the normalization comes in. You see this activation come in, and then there's this thing called dropout. So dropout is a concept where we actually randomly turn off a number of the neurons in the layer. The reason we do that through sort of every training pass is we randomly turn off a number of the neurons is so that the other neurons sort of have to fit better around the other neurons. So you can think of it as like you're daydreaming and you're doing your job and it works, and then maybe if you have to do your job extra well one day, you have to focus all your attention. It's sort of the same thing. The reason we introduced dropout is so that their model doesn't overfit, so it doesn't learn too well certain attributes about our data that we're feeding in that may not be optimum. For instance, we could have a bad randomization, we could have a whole bunch of other problems. By adding dropout, it essentially balances our model better, balances the neurons in that layer of the model, or between the layers of the model, essentially. Okay. This really helps very well with overfitting. So, and that overfitting problem happens often when we add a whole bunch of neurons to our model, because the neurons essentially will start to remember our data itself, which is problematic. We don't want our neurons to remember the specific data. We want our neurons to generalize across the data. We want our neurons to learn across the data, essentially. Okay, and then this is max pooling, dropouts, normalization, etc., all that good stuff. And then at the end here, we have our dense layer. If I run this down, you can see now our model has expanded significantly with more layers and parameters and stuff like that, and we're 1.6 million, so not so much, but a few more layers and stuff like that. And if we look down here, I guess it's already finished training. So it's already finished training. I scroll down. You can see through the benefit of all that stuff, I haven't really picked up very much, but you can see now my validation and accuracy are better, but I haven't really got a much better accuracy. So adding those additional layers probably weren't that optimum, but this is just one of those things you need to play around with, is these types of things. The type of filter, the size of filter really depends on the data to a certain extent, at least in convolution. There is other methods called attention that are coming out that either in some cases circumvent or work with convolution. That's an advanced thing. I do have an example of that, or wanted to get into that later, but we're running out of time here really quickly. So let me jump back into the slides. Okay, so that's all that. Again, so I'm just adding that one convolutional layer to that example as a way of better identifying our images itself, or better identifying the features in our images, right? So, okay, so now we want to go into a topic of adversarial learning, which really starts with autoencoders and talks to stuff like generative adversarial networks, or GANs. So if you ever heard anything about deepfakes or that type of thing, we're actually talking about GANs themselves, or generative adversarial networks. And I want to sort of get to that point where we can talk about how a GAN works. So I'm going to go a little quick. So what I typically do at this point is break you guys all out into a group, but maybe we'll just do this for a quick minute to see if maybe somebody can pick out the example of this. So this is the autoencoder game. So essentially we take and expand the perceptron game, and now we introduce the concept of an autoencoder. An autoencoder is essentially a type of unsupervised learning where we're going to feed a set of images here on the left, that set of familiar images of the filled, mixed, and empty, into our network, and it's going to decode the image down to some encoding. This is going to be a single value encoded, and then it's going to, from that value, it's going to unencode it and regenerate those images with no loss. So we should see exactly the same images. The problem here then is to find the weights that can balance this problem. So if we feed these images in, they come out exactly the same. The one caveat we have here is now we're using a 0.5 step activation function. So in this case, if a value is less than 0.5, it comes out as 0. If it's greater than 0.5, it's a 1. Okay? No exceptions. So less than 0.5, 0, greater than 0.5, it's a 1. Okay. So in this game, you just roll your weights and try and pick your values. I'm going to let you guys sit on this for a second and think if you can search for or understand the weights. I'm going to give you a hint. You probably already have this part solved. So Jesse, we'll just give you a second here. Normally, I would do this type of exercise in a group of like 3 to 5 people. 3 to 5 people would gather and work on this together, trying to solve this, because you could use three mats essentially, and then 3 sets of dice to balance the weight problem as well, and 3 minds or more minds to help. It's not entirely that difficult, as long as you understand, or you kind of understand the trick between this and then getting to this point. That's my one clue. Okay, has anybody solved it? I don't have the chat window open. Has anybody solved it? No? Oh, the one question here in the chat here is 3 times 3 plus 1. Remember, the plus 1 is for the bias. It's always for the bias. We always want to add plus 1 for the bias. Does anybody have the answer for this? So, I'll just go to the first. Okay. So we can go back to the first problem we looked at when we first solved this, is that if we use the weights that we first use, we can encode these values down to 0 to represent our empty, 0.5 to represent our mixed, and 1 to represent our top. Now, using these values, we can just decode them into what our proper value should be. So if a 0 comes out, 0 times whatever weights should equal 0. So that shouldn't be a difficulty, right? What it turns out is, using the step function, is if we put a weight of 0.1 and 0.75, we can actually solve the problem. So the trick here is that the middle mixed value is always coming out as 0 as the bottom, right? We don't have the opposite of 0.1. If we did, we would have a different problem, because we'd have 4 images to classify, and this only works well for 3. So in this case, you can see if I put the 1 and 0 through the encoder, the 1, 0 comes through as 0.5 in the middle, and that 0.5 value is going to come out to this first perceptron. 0.5 times 1 is 0.5, but since it's hitting the step function, it's going to come out as a 1 on the top. And this 0.5 comes through times the 3/4 equals half that, and then comes out as 0. Yeah, sorry, I didn't mean to go to the top image. I meant to go to the middle image. Yeah, so this comes out as 0 as the next. So if this 1 times 1 comes through, which will equal 1, 1 times a 1 equals 1, and 1 times 3/4, which is greater than 0.5, is going to give us a 1. And likewise, if I do the same for 0, it's just going to come out 0. So that's how autoencoders work. We typically could consider this a unsupervised problem, and the reason for that is because the only loss we're pushing back through the network is how badly it picks between what the image going in is and the image coming out. And we will typically do that by something as simple as taking the difference between the values. So for instance, if I was shooting in an image of 1, 1 in, and I was getting an image of 1, 0 back, I would just simply say that my loss is 1 going back, and that loss of 1 would probably be applied to this perceptron and going back through the network. You couldn't use the update equation for this because even just this simple layout is too complicated. You'd have to use something more complicated, like backpropagation, or, well, I mean, you could use anything, genetic algorithms or particle swarm optimization or anything. But once you understand how to get to the encoding piece, building up this part here shouldn't really be that difficult. Actually, in a game scenario, we had more time, it would probably be easier. So I show, there's a good example of DLB fashion autoencoder in my example set that shows how this works. And remember, the only thing it's doing is it's taking the input image and it's comparing it against the output image, and its determination of loss is how much it's off by that image. So if this value here is absolutely white, say a value of 255, and this value is coming back as 200, the loss was essentially, and I'm very much simplifying, but the loss would be a value of something like 50. But keep in mind that we're modifying this input of 255 by divided by 255, so the same would be done backwards. I'm not going to spend too much more time on this because I want to get into generative adversarial networks, but any questions on this? And I encourage everybody to look at this example. This is one of the first things that a lot of people will learn or they'll spend some time on because it's sort of fundamental to how we learned, the upper levels or upper ways we can use deep learning. And a lot of that hinges on understanding how this encoding works. Now, this encoding in this case is the same as our classification, but this encoding, we could have 1,000 input neurons here that encodes this down to just 20 neurons, for instance. Those 20 neurons would be a simpler representation of those 1,000. That simpler representation we could use for numerous things. It could be used to rebuild stuff or find the distance between things or find variation between things, et cetera, et cetera. I'll show you how that works and how that understanding the latent space or the encoding space in networks is something we do in GANs, okay? This is an example of the autoencoder model from that last DLB fashion autoencoder. And this is where, so the model in this case is going to be a little different. We're building up encoding layers. So these encoding layers actually just represent this piece here. So this first piece is the encoding. And then the decoding architecture is that second half of the model. We essentially combine those two pieces of the model and we fit them into the model, and then we can summarize. So we put this all together as a model, and we would train it all together as a model. So we don't train this separately, we would train this all together as a model. The loss coming out here is something we push back through the whole model, okay? That's some of the cool stuff we can do with deep learning, okay? And here's a picture of what that model actually looks like. You can see that for the autoencoder example that we're looking at about 50,000 parameters, so not really too bad as far as training. And really all this is doing is sort of encoding the image down to that encoding space and then decoding it back up. Okay? And then from that example, you can see our training results. Now you can see the test and validation are really pretty tightly tied, and you would sort of expect that to a certain extent on an auto-coding example. The important thing to realize here is the loss is still pretty high, so that the images don't look exactly like they should as far as decoded. We'd probably have to train it for more generations, etc. But the amount of loss will show us how close we're getting to an answer. So if we can reduce this loss to 0, we would expect the generated images to almost be perfect, right? That's essentially what the loss would mean in this case. Okay, so let's go on quickly to autoencoders to generators, GANs. And I'm going to run through the last little bit here because I want to leave you guys an example you can play with later. I find that most people, they learn really well afterwards if they have something to play with. So I always try and leave people a good example that they'll be compelled to play with. And the example I have is I think you'll all feel compelled to play with, but we have to get to it. So, so from autoencoders, we can get to generators. So in 2014, young gentleman, Ian Goodfellow from University of Montreal developed the generative adversarial network. You notice I have a common theme here that a lot of these guys are Canadians, eh? Yeah. Okay. Uh, created the generative adversarial network. And the concept here is that you have two networks. They're essentially fighting against each other. You have a generator network and a discriminator network. The generator network is essentially going to do what our decoder was doing before, and using some sort of latent space or random space to build fake images that can trick the discriminator or the critic network into believing they're real. The critic network is trained on real images to understand what a real image looks like, but they're trained together and they start training off at the same time. But because they're starting to train at the same time, the discriminator doesn't know what is real or fake. And it's by learning what real or fake is it gives the advantage to the generator to learn with it, to sort of learn how to fool it better, sort of thing. So essentially it's sort of a war of races, you could say, that the generator is trying to get better at faking images and the discriminator is trying to get better at defining real images. Okay, and this is often compared to a detective or a art critic and a forger or generator. It's sort of the very similar sort of analog to this sort of model, where the detective is trained on the real data and the forger tries to create a fake that will fool the art critic, essentially, right? And they can produce some incredible results. So these are some examples of GANs. Now, this isn't just a simple GAN or vanilla GAN. This is a face scan, essentially. There's a couple of things that go into sort of producing these things. On the one side is a face scan where you see a deep fake of everybody's favorite star being replaced on the side, or there's Obama being replaced by Jordan Peele through not just the face, but through actions, and be actually able to control its all movements. In the first example, you can see that we're just overlaying the face over top of the image, but in the second example, Jordan Peele's example is actually controlling the movements and actions of the president's image there. Okay. On with GANs. Some other really interesting examples that we can start to do with GANs as well. And this all really hinges on being able to understand that latent space, and being able to map across that latent space is allowing us to do that. So that ability to learn or encode pictures down to some latent space that we can understand variations between other pictures allows us to do this sort of cool stuff here. It allows us to sort of map across these latent spaces that can match other latent spaces, so we can essentially learn other spaces, so we can learn what those spaces should look like and then apply them to these images, essentially what we're doing, which is really cool. Okay. Here's another example where we have deep fake of Back to the Future with Tom Holland and Robert Downey Jr. It's very, very well done. This was just released about a month ago. But this is the type of stuff you're getting out already. And really this sort of begs the whole question about what's going to happen to our media of the future, right? Like you could take, for example, Netflix and streaming services and stuff like that. What's to prevent something in 5 or 10 years from you being able to say on Netflix, well, I want to see this movie but with these stars, or I want to see this movie with this person or that person or whatever. And this might become a reality sooner than later, but it's really interesting. It opens up all sorts of interesting things with fake news, other fake data, fake manipulation. I mean, it's difficult for us to determine this, so now what we're doing now is actually creating GANs and other adversarial training pieces that are trying to determine how to determine these fakes, essentially, right? And you know, there's essentially little detective pieces in these images that can give us clues, but they're getting really, really good. And a lot of it's the technology is advancing so quickly. Okay? And it's even producing art. Here's an example of a piece of artwork that was essentially just a vanilla GAN that was trained on a whole bunch of art. And this, you can see the signature here is essentially the GAN equation. This equation, we use a math to define a GAN. And as a signature in this piece of artwork sold for 410,000 euros. I think it was probably an investment auction, but needless to say, it was to make some waves and news. Okay, so I have this concept of the GAN game as well. We won't do it now, but the GAN game is sort of the same thing that we've done with the autoencoder game, except it's backwards. So we sort of we break apart the GAN, and now on this side, the discriminator becomes the encoder. Okay, so the discriminator essentially becomes our classifier, and discriminator can become a really good classifier. Keep in mind that we have two models here in our GAN. So in the one side here, we have the generator or the decoder. So in our autoencoder, this was on this side, and the encoder was on this side. So we're essentially just reversed this. We flipped it around, and now the generator creates images. The images that we're feeding into the discriminator determines if the images are real or fake, how real or fake they are, and that loss is then getting passed back to both the generator and the discriminator. So in the case of the generator, if the generator generates a real image, it's going to get praised. If it's generating a fake image, it's going to get some loss back. Likewise for the discriminator, if the discriminator gets a real image, it's going to get praised. If it sees a fake image, it's going to get loss pushed back. If it allows the generator to pass a fake image through, we're going to push some loss back. We're essentially going to punish it. If the generator or the discriminator identifies fake images that the GAN is trying to produce, we also praise it as well. Okay, so we're just flipping it around essentially. The autoencoder, we're just flipping it around, breaking it apart and flipping it around. That's essentially all we're doing. So in this example, if we were to use those same weights, we would just see the same weights in this example would sort of satisfy this same problem for a perfect generator and discriminator GAN for this model. So, and the way this would work is we just roll one of our random values. If it was a 2, we would just re-roll it because all we really want is 0 to 1 as our inputs. Remember, it's just a random input we're feeding into our GAN. GAN generates a thing. All the GAN is learning to do is how to balance these weights and to generate what looks like a possible correct image. That's all it's doing, right? And the loss is getting pushed back so that it generates that proper correct image, and it learns how to map that latent space. So essentially that's what they're learning how to do, is to understand that latent space. Okay? Again, this is the diagram of the networks. And the nice thing about the discriminator network, and I've used this before myself, is the discriminator becomes a really good classifier on its own. So if you have things that you need to classify on real images, you can actually break your GAN apart later and actually use just part of the discriminator to classify your stuff, or the generator to generate images. GANs are notoriously very difficult to train, though. I should mention that. So oftentimes we'll just use built-up examples, more often from not, because they're can be very complex in models and stuff like that. So I wasn't sure on what sort of audience we would have, Jesse. I also introduced GANs for medical imaging. There is probably 150, I think, out right now that cover all forms of medical imaging. Here's a GitHub catalog, essentially, of all of them with papers and code sources and stuff like that. If you feel like you want to pass that around, it might be useful to others. I won't go through that list at all, but we can go through some other examples here quickly. Okay, so this is essentially the way the loss is calculated again. I won't go into this too much. But other applications of GANs, for instance, all sorts of applications for GANs. We're just finding new applications all the time. GANs essentially are quickly taking over the world. A lot of deep learning was used previously for classification, face recognition, stuff like that, but it's really, deep learning is really morphing into more of a GAN thing. It's really more of a generator, adversarial learning. It's really more about crunching these types of large sets of data, like images and so forth. A lot of medical stuff as well, like I mentioned before. Okay, so let's just quickly go through here some examples of GAN. So here's some types of GANs. We covered the big GAN earlier. Big GAN is really an example of a conditional GAN, and I'll touch on that really quickly again here. Couple GANs, feature loss GAN, simulation GAN, cycle GAN we'll look at, pix-to-pix GAN, we'll look at a variation of an attention GAN. I'm just going to look really quickly at these samples. They're all in the GitHub repository you can look at. You can open them up and train them. I'll just quickly go over them. And I won't go into this GT GAN, but these are all just types of GANs. The types of GANs are really based on the type of training that you do and how you train them. So GANs are typically trained what we consider unclassified, but in some cases you might do supervised. So example of supervised GAN would be pix-to-pix. We'll look at one of those. An example of an unsupervised and multimodal GAN would be a cycle GAN, for instance, and we'll look at an example of that as well, and what type of sort of training goes into. Okay, and then really it's all about understanding the latent space. So here's an example of a GAN that's learned faces. Looks like celebrity faces. So at the top here, we have a celebrity face, a male celebrity face with glasses, and at the bottom we have a female celebrity face without glasses and smiling. You can see the transition across various different vectors. And remember, keeping in mind this is only 2 dimensions. If we had more dimensions, we could really define more dimensions. But this really gets what I'm talking about, is understanding movements across the latent space. Now, in some cases, those latent spaces are going to be garbage, right? Like some of these aren't going to make a lot of sense. They're pretty ugly. You only have one glass on one side in some cases. But in many cases, these latent spaces or these generated images do make a lot of sense, right? And that's the piece we're looking at. Any questions there? No? Okay, so let's look again at the example of the conditional GAN or big GAN. I'll just open it up. Okay, so I'm just going to open the big GAN example. Okay, I'm just going to say runtime run out. And this one should run pretty quickly. In this example here, I'm just using a pre-trained model. So essentially, this is just a pre-trained model. It's already got set weights. We don't have to train it at all. GANs can take a very long time to train, 3 days to weeks to months, and I'm not kidding. That's why we definitely GPUs or even TPUs, TensorFlow Processing Units, which are essentially an advancement by Google on their TensorFlow stack that allows it even faster. The order of magnitude might even be 10 times increase. On Google Pro, they say it's Collab Pro, they say it's usually double performance. I've noticed in some cases doing side-by-side comparisons between accounts, sometimes up to 20 times performance. So Pro to me seems to be worth it. It's only $10 a month. So if you're doing a lot of collab stuff or you're doing a lot of exercises like this, it may be worth it in some ways. So here we're just doing a generation. So now all of this stuff up here, all this code up here is just for showing the data itself, the one-hot encoding and all this stuff. This is all just really showing the data, so we won't go through it here. So remember, remember this is a generated image. Remember, it's generated this time based on conditions. So in the latent space itself, we learn the latent space in such a manner that we can understand conditions itself. So if you think back to our original GAN or original autoencoder, for instance, when the classes came out of filled, mixed, or empty, we just pushed the images essentially back through, not worrying about the classes. In a conditional GAN, we might worry about the classes or other attributes, which allows us to train the GAN itself on classes. Now, since this GAN has been trained on classes, I can change those classes in order to generate other images. So if I go through here, I can generate, for instance, a sports car, and then just click Run. After I run this once, as soon as I change a class, it'll do so automatically. So not bad. the middle image is a little mixed up, but overall, I mean, some of these images would look real, right? But, you know, bear in mind, they're not real at all. They're just composites of what the machines learn. So if I look at some good examples of bad examples, I should mention, are anything that's with a face. Animals are sometimes good examples of bad examples. So if I go Persian cat, for instance, let's see what that looks like. Okay, so overall, I mean, not too bad, but you can see a few things like the eyes here is a little funny. Some of these other examples, if you run through or do other classes, you'll see some good examples and some bad examples. Really, it varies on the type of training and the type of images that were trained and the variation of images themselves, right? So if there's a lot of variation of images, human faces will have a lot of variation. I'm just seeing, there was like a guitar here, electric guitar, this is a good one. Yeah, so there's an example of an electric guitar. And you can imagine, even though there probably was a whole bunch of images being trained, there's a whole bunch of variation in those images. It's just training more or less that this is a guitar. It's classifying it as a guitar based probably on this. It's not so worried about the other features in the image. And that's a problem in this example, right? It's not really looking for, oh, it has to be a person playing guitar, for instance, or something like that. So that's a problem with GANs to a certain extent, is you have to watch your training sets and your training data. Okay. Let me just jump back to the slides. Okay. So some other examples of GANs are paired and unpaired. So paired are like a pix-to-pix scan. So you might have an example of a picture, an X picture as your input, with an expected output. But we'll feed the GAN both these images to let it know that when we feed this type of image, we expect this type of image, right? Similarly, if we feed this, then we expect this. So this is sort of a supervised GAN, okay? And in the pix-to-pix example, so let me quickly run that. I'm just going to open that. I'll just open the pix-to-pix, and then I'm going to go in here, and I'm going to open the next one and run it. The next one we'll look at is the cycle GAN. Yeah, it seems to be taking a while to load. I have noticed if I get too many sessions, sometimes it goes, oh, there we go. Okay, so let's just go on, check your runtime type. And with these examples, you want to make sure you're running a GPU for sure. There's a lot of weights in these models. So this model is not pre-trained. This GAN we're looking at, and what we're going to do with this pix-to-pix model is train it. So remember that what we're doing is essentially taking input images and we're training it so that it looks like output images, right? So we're essentially training it on a pair of images. Our input we want to simulate and the output we want to expect. And in this case, we're using cityscapes. Okay. Well, I'm not sure if this is because I have too many models or. Looks like it stopped somewhere. Okay. So it stopped somewhere. I'm just going to go down to where it stopped, and my computer's all of a sudden gotten quite slow. So here's an example of the images we're feeding in. So this is essentially our source that we're going to be feeding in, and this is our expected target. So what we want to feed into the GAN is an image like this, just to say this is a car, This is a building, trees, etc. And then we wanted to generate this image here. That's the perfect image we wanted to generate. And that's this data set we're training it on. Okay? And there are all these functions, and they're just basically normalizing. We apply some jitter or randomization to the images itself. Okay, and then there's all of this is input pipeline. You can see it really is, not to be too intimidated, a lot of this code is plumbing code, and really the whole model is here. So this is the generator, and we're using something called a UNet, so that's just a different sort of convolutional setup of data. Like I said, this is a bit of an advanced example, so I've sort of gone from 0 to 60 in this tutorial. You can see this is the model itself is quite big. And then here's a generation of our first output. And as I scroll down slowly again, here's an example of the loss output better. If you want to spend some time looking at that, that's in the image, it's in there. Here's an example of the discriminator model. You see it's a little more detailed as well. And we're using images here of 256 by 256 pixels with 3 channels. So we're using all color channels as well. In the fashion example, we're only using 1 channel. Okay? So now it's trained, or not trained, so it's run through and it's predicted an image. You can see it's sort of partially predicted, but it's not by any means predicted anything of any sense. So that's its first run. And now I'll just go through, and here you can see it's training, so it didn't stop on me. So this is, and we'll watch it train for a while. And remember, it's being fed batches of images. So you'll see the training output if it pauses. Normally it pauses a little longer. Yeah, so if it pauses long enough, you've glanced at it enough. Jesse, I'm not sure if you're seeing these flashes of the images. They're staying up for about a second sometimes. But what you can see is how the generated output is trying to match the ground truth. And you'll see the predicted image. And you'll see in some cases, there's variations in that image. I'll hold it here for a second. But if you're running the sample, you should be able to see this a lot more clearer. So hopefully you're running the sample. And all you have to do is just say runtime, run all. Okay, good. So I'm not going to jump back to PowerPoint. I'm just going to jump back to the cycle GAN. So the cycle GAN is essentially a step up from PIX to PIX in that it uses cycle consistency. And cycle consistency is where you can think of it as if I was to translate an English sentence to French, and then translate that French sentence back to English, how much discrepancy might be in that translation? That's essentially the cycle consistency. I can determine, say, that translation from French back to English, how wrong it was, and based on how wrong it was, punish my model or correct my model appropriately, right? And that's essentially what a cycle GAN does. So let me just go through here, and I'm going to run this, run all. Okay, we're just going to, yeah, so Collab only allows you to run, I think, normally 2 sessions. I have Pro, so I can run 4 sessions. So I'm just going to kill a bunch of these other sessions. Terminate my PIX to PIX, so we won't go back there. And I'll just run this. The nice thing about the cycle GAN is you don't have to give those pair-to-pair translations. You're not training it on the pair-to-pair translations, but you are giving it a sort of an expected output to train to. So as much as they refer to it as unsupervised learning, it's really more semi-supervised learning. And this first example here is essentially just this pip install is installing one of those prerequisites. In this case, the examples. Some further examples from TensorFlow. In this case, it's the cycle GAN data set. And there's a number of cycle GAN data sets. I think the original one was published with a horse and zebra, where it colorizes horses as zebras in images. In this example here, I've converted it to use maps. So this is what it's doing, is just pulling down the map data set, and then we're going to train on it. Okay. What I'll do is I'm going to open up and jump to, just going to keep that running. Yeah, so here's an example of that UNet architecture I was talking about in the Pix-to-Pix. And this is where we're getting an image, being able to extract more of those features and identifying those features. So one of the things in convolution is that it really only extracts localized features or features around pieces in the image. We don't really have any sort of global identification in themselves. And we can correct that with this thing called attention. Okay. So attention itself is a new method we're using in deep learning that allows us to focus or understand how a feature interacts globally with the rest of the environment. Now, attention and transformations, and this attention transformation model is being used in things like BERT. Bidirectional encoding for representative transformations is what it comes out to. It's by Google for this natural language understanding, natural language programming, or sorry, natural language, for being able to parse, natural language parsing of language and being able to generate new language using these models called BERT, or these attention transformation models is what they're using.
Natural language generation, eh? NLG?
Yeah. And this is, Google held this model back for the BERT model. They held the BERT model back for almost, I think it was 8 months, because their fear was that people would be using it to generate fake news. A really good example of a BERT model, or a type of BERT model, is AI Dungeon 2 uses a similar model. It's a game now being promoted. If you want to see how one of these things work, you can play it sort of like an adventure game, like the old Tex Zork adventure games. Really good example of that. Okay. The reason why I mention this attention is because this attention is now being used in a new level of GANs called self-attention GANs. And we use this attention to address finer grained details in the image and to extract better details in the image itself. So this allows us to do some really interesting things using that attention and being able to identify things in models and generate better models themselves. So what's come out of this is a young man named Jason Antic, who's just a self-proclaimed programmer, took this concept of the self-attention GAN, which essentially regulates its attention of itself against what it needs to learn, and he turned it into sort of a colorizing model. And what you see here is a bunch of old clips of movies, black and white, and one black and white image is Psycho, being colorized. And he's built this model, and I'll show you to you in a few seconds here, of how to colorize old images, photos, and videos. You can see there's still some problems with the model we're working with, and the colorization in this example is he's using a model called Artistic. And keep in mind that the images and the colors and stuff like that are all based really on the models or the information it's trained on, right? The data, the images it's trained on. You can see in this example, the Psycho example, the hand here is sort of matching the wood of the door. It's called that sort of ghost skin, where it sort of doesn't blend well, or it doesn't identify the skin very well. And this is sort of where it's sort of lacking the notice of the attention or identifying those features, right, of the image itself. And that's one of those things. So some problems, but it's gotten much, much better than we've seen previously. Okay. And here are some more examples of Deolify, and I've published on LinkedIn a number of examples of videos and other stuff. It's a really cool thing to work with. So let me just go back to the cycle GAN. And I'm just going to walk through that quickly, and then we'll finish really quickly up with the Deolify example. So this is the cycle GAN, and this piece here is just, again, talking about how it's using that cycle consistency to generate the models. The model it uses, or the models it uses itself, are just based on Pix-to-Pix. So it's essentially using the same model as the Pix-to-Pix. It's just the training procedure is a little differently, and the way its loss is calculated is a bit differently. It just works in a cycle, that cycle consistency. It sort of does this back and forth, forward cycle and backward cycle, essentially. Okay, and I'm just going down to demonstrate the training. So you can see here, there it's training on that map image. You can see it's the generated one on the side. What it's trying to generate is a road map of that same image. And you can see this has only been training for, what, a few minutes now, but it's already coming out not too bad. And, you know, we might train this for a couple days to get it better, but once it's trained, once we feed it an image, it should be able to generate a road image for, you know, whatever we expect based on an aerial image of whatever. So that's an example of cycle consistency, or cycle GAN. So let's look at Deoldify as the last example I'll lead you with. So I'm just going to go to Deoldify, Google. And it's usually the first link. And on here, he's got a couple notebooks and other examples. Okay, he's got various ones on artistic, stable. These are all notebooks. Really what you want to grab, though, is the one that's marked collab, and that's really designed more for collab. So I'm just going to grab this image colorizer collab notebook. Okay, and they've been keeping it fairly updated, so it's in pretty good shape. So I'm just going to click on it. Okay, so I'm on the repository of the Deoldify site. I'm on the image colorizer collab notebook, and I'm just going to open it in collab by clicking the blue button. Okay, and I'm just going to connect my runtime. Just click that connect button. Again, I'm just going to make sure my runtime is set up as a GPU. That's good. This example is using a pre-trained GAN, so it doesn't necessarily need to use a GPU, but it's just going to make the example simpler. This example also uses Torch, but again, we're using a pre-trained model, so the amount of exposure you're going to be using to work with Torch is pretty minimal. Really, it only boils down to, I think, these few lines where it's just telling it to use a GPU instead of a CPU. That's all. Otherwise, it's just normal Python. So in order to do this, what we have to do is just come down here, and we have to find an image that I want to colorize. So I'm just going to go to the recommended image sources at the bottom of the page in the way we work. Click that. And you can use any link to an image. I often use Dropbox, for instance, for other images. My mother has me going crazy with the old images and colorizing them. So let's use this image here. So I'm just going to click copy image address, go back, whoops. The bar doesn't want to move.
If you, they should have a little button on the very far right side that you can click.
Yeah, I got it. Oh. Okay, so I pasted the image URL in, and now I'm going to run the code. So I'm going to run all the code, and it's going to probably give me this notice, but I've ran this lots of times, so I'm not worried. If you have concerns, just look through the code. It's going to be one of those things, I guess. So what it's doing is it's pulling down the whole source code from Deoldify, and it's just changing the directory of Deoldify. It rebuilds the code up that it needs to, sets up requirements that it needs to, imports any of the components it needs to. This piece here, it's importing the trained model. In this case, we're using an artistic model, the artistic version, and it pulls it down pretty fast. This is a large model as well. And then we're going to pull down some other colorization weights, I think, or whatever, I guess. And then down here, okay, so it should be training. And it takes about a minute for a 30-second video, I guess, or less in some cases. For this, it's not too bad, but look at our results here. And example. So remember, this is a generated image, right? This is a generated image based on this original image. What it's done is it's taken this image, compressed it down into some latent space, and then generated it back up. And the ability that gives it to pick out these fine details under the cheek and the hair and all this stuff is that attention mechanism. If we were using straight CNN or convolutional neural networks, we probably wouldn't get these details. But you can see we still have a few artifacts. You can see her fingers here are sort of badly colored. It's not picking out those details quite enough yet, so a little bit of training. But those guys are working on it. This has become big business for them, as you can well imagine. They're looking at making this available for old movies and other old media and stuff like that. Should be exciting. So that's what I'm left with, guys. So take that with you, and I hope you guys have fun with it. Thank you.
Thanks so much, Michael, for your presentation. It was really good and such interesting content and ideas. So, thanks so much.
Okay, thank you.
All right, everyone. Thanks so much. We'll have our next presentation on the third week of April. We've got a speaker coming in from the U of C named Mr. Abdullah Sarhan. So we'll go from there, and I hope you have a great month.
Okay, be safe, guys. Thank you.